Hello and welcome to Space Historians. I'm so glad you've joined me tonight, ready to let the day fall away and drift into something far larger than the hours you've just lived through. Tonight, we're travelling outward. Not quickly, not with urgency, but with the kind of patient curiosity that allows you to truly see. We're going to ask a question that seems simple, but turns out to be one of the most beautiful puzzles in all of astronomy. How far does the solar system actually reach? Before we begin, I'd love to know, where in the world are you listening from right now? And what time is it where you are? It's always amazing to me how the night sky looks different depending on where you stand on this spinning planet. And yet the same stars have watched over every human who's ever lived. If you enjoy these slow journeys through space and time, a like and subscribe help keep this channel floating steadily through the cosmos. And for those who've already joined this quiet constellation of listeners, thank you. You're part of this voyage. Each episode here is about more than facts and figures. It's about the stories hidden in the darkness between worlds, the human moments of discovery, the mysteries that remain unsolved. Tonight, we're going to explore distance itself, tracing the sun's influence outward until it dissolves into something larger. So, as your breathing slows and your thoughts begin to wander, imagine yourself stepping away from Earth. Slowly, gently, the blue fades, the air thins, and ahead of you stretches a frontier that doesn't end sharply but fades like a sunset, layer after layer, until you can no longer tell where one thing stops and another begins. If you tap that notification bell, you'll always know when the next journey begins. But for now, you don't need to do anything but listen and let yourself drift. Let's travel together, outward from the warmth of the sun, into the shadows where distance becomes almost meaningless, where time stretches into millions of years, and where the question of boundaries becomes a meditation on what it means to belong. Welcome to the quiet edge of everything we know. On August 25th, 2012, something extraordinary happened in a place so remote that sunlight takes more than 17 hours to reach it. A spacecraft barely larger than a car, launched 35 years earlier, crossed an invisible threshold more than 11 billion miles from Earth. Its instruments recorded a sudden change. The density of plasma shifted, the hum of particles from the sun faded, the whisper of the galaxy grew louder. Voyager 1 had done something no human creation had ever done before. It had left the bubble of the sun's influence and entered interstellar space. The announcement didn't come until a year later, in 2013, after scientists had confirmed the data again and again. But the moment itself, that quiet crossing in the darkness, marked a turning point. For the first time, humanity had touched the edge of the solar system. Except, the solar system didn't actually end there. Voyager 1 was still bound to the sun by gravity, still orbiting it in a slow arc that would last for tens of thousands of years. In one sense, it had left. In another, it would never leave. And that paradox, that strange truth, is at the heart of the question we're exploring tonight. How far does the solar system actually reach? It's a question that sounds simple, the kind of thing you might expect a single number to answer. But the deeper you look, the more complicated it becomes. Because the solar system doesn't have one edge. It has many, layered like the rings of a tree, each one defined by something different. If you measure by planets, the solar system ends at Neptune, the eighth world from the sun, orbiting at about 30 times the distance from Earth to the sun. Beyond Neptune, there are no more giant spheres of rock or gas sweeping through space in tidy circles. But if you measure by smaller objects, icy bodies left over from the solar system's birth, then the boundary stretches much farther. The Kuiper Belt, a disk of frozen worlds including Pluto, extends to about 50 times Earth's distance from the Sun. Beyond that lies the scattered disk, where objects follow elongated paths that carry them hundreds of times farther still. And if you measure by gravity, the reach of the Sun extends almost unimaginably far. Somewhere out there, perhaps a light year away, maybe two, there may be a vast shell of icy fragments called the Oort Cloud. It's never been seen directly, but the comets that fall toward the Sun from every direction suggest it's real. If it exists, then the solar system's true diameter is nearly 4 light years, almost halfway to the nearest star. Then there's the heliopause, the boundary Voyager 1 crossed. It's the place where the solar wind, a constant stream of charged particles flowing from the Sun, finally stops and gives way to the star, interstellar medium. By that measure, the edge is about 120 times Earth's distance from the Sun. So which is it? 30 times? 50? 120? Thousands? Or nearly 2 light years? The answer depends on what you're measuring, and that's what makes this question so fascinating. The solar system isn't a neat bubble with a single wall. It's a series of overlapping zones, each defined by a different kind of influence. Light, gravity, wind, magnetism, debris. Each one fades at a different distance. To ask how far the solar system reaches is really to ask, what does it mean to belong to the Sun's domain? Is it about orbiting the Sun, or being shaped by its heat, or simply existing within the reach of its gravity? Tonight, we're going to explore those layers one by one. We'll travel outward from Earth, past the familiar planets, through the icy belts and scattered populations, across the heliopause where Voyager made its crossing, and into the ghostly realm of the Oort Cloud. Along the way, we'll see that the solar system is far stranger, far larger, and far more beautiful than the simple diagrams we learned as children. Because the truth is, the solar system doesn't end where the textbooks stop. It extends into places so remote that sunlight is no brighter than starlight, where objects take millions of years to orbit once, where the boundary between what belongs to the Sun and what belongs to the galaxy becomes impossible to draw. And in exploring that truth, we find something deeper. A reminder that boundaries are human inventions. Nature doesn't draw sharp lines. It fades, blends, and overlaps. The solar system is not a box with walls. It's an influence that spreads outward like ripples on water, growing fainter with distance but never quite disappearing. So as you settle in tonight, let yourself imagine drifting outward with me. We're not racing. We're gliding. Slowly, patiently, watching the Sun shrink from a blazing disk into a bright point, then into just another star among billions. And somewhere in that journey, between the warmth of Earth and the cold of interstellar space, we'll find the answer. Not as a single distance, but as a story. A story about how far a star's influence can reach, and what happens when that influence finally fades into something larger. The solar system, it turns out, doesn't end. It simply becomes the galaxy. If you want to understand how far the solar system reaches, you have to start close to home. Here, on Earth, orbiting at what astronomers call 1 astronomical unit from the Sun. That unit, that single measure of 93 million miles, becomes the ruler by which we measure everything else in the solar system. It's the distance light travels in 8 minutes and 20 seconds. It's the space between us and the star that gives us life. From this vantage point, the Sun dominates everything. It fills the sky with light. It warms the oceans and stirs the atmosphere. It drives the seasons and governs the rhythm of days. To live on Earth is to live inside the sun's immediate influence, so close that its power feels absolute. But even here, at 1 astronomical unit, we're already witnessing something profound. The sun doesn't just shine, it breathes. From its surface, a constant wind of charged particles streams outward in all directions. Electrons and protons, torn from atoms by the sun's immense heat, race away at hundreds of miles per second. This solar wind is invisible to our eyes, but its effects are everywhere. When it reaches Earth, it collides with our planet's magnetic field, creating shimmering curtains of light near the poles. The aurora borealis in the north, the aurora australis in the south. These glowing displays are proof that the sun's influence extends beyond light and heat. It touches us with particles, with energy, with a constant flow that shapes the space around our world. And the solar wind doesn't stop at Earth. It keeps going, past Mars, past Jupiter, past Neptune, farther and farther, carrying the sun's presence into the outer reaches of the solar system. But let's not get ahead of ourselves. Let's stay here for a moment, on Earth, and consider what we know. We know that Earth circles the sun once every 365 days. That orbit defines our year, the foundation of calendars and seasons. It's predictable, reliable. The same cycle has repeated for billions of years. We also know that Earth isn't alone. 7 other major planets share this space, each one orbiting at its own distance, each one taking its own time to complete the journey. Mercury, closest to the Sun, finishes its orbit in just 88 Earth days. Venus takes 225. Mars, just beyond us, needs 687 days. Then come the giants. Jupiter, 11 times wider than Earth, takes nearly 12 years to orbit. Saturn, with its majestic rings, needs 29. Uranus requires 84. And Neptune, the farthest of the 8 classical planets, completes its orbit once every 165 years. These are the worlds we've known for centuries, mapped by ancient astronomers and confirmed by modern telescopes. But even as we list these planets, we're already seeing the first hint of the question we're exploring. Because Neptune, at 30 times Earth's distance from the Sun, was long thought to be the edge, the final outpost, the place where the solar system stopped. That belief held for more than a century. From Neptune's discovery in 1846 until the late 20th century, astronomers assumed the planetary system simply ended there. Yes, there were comets that came from farther out, suggesting something lay beyond, but no one had seen it directly. Then, in 1930, a young astronomer named Clyde Tombaugh discovered Pluto, a small, icy world orbiting even farther than Neptune. For decades, Pluto was celebrated as the 9th planet, the new edge of the solar system. But Pluto, it turned out, was not alone, and its discovery was only the beginning of a much larger revelation. In the 1990s, improved telescopes began revealing other objects beyond Neptune. Dozens at first, then hundreds, then thousands. Small, icy bodies orbiting in a vast belt that stretched from 30 to 50 times Earth's distance from the Sun. This was the Kuiper Belt, a region we'll explore more deeply later. But for now, what matters is this. The discovery of the Kuiper Belt proved that the solar system didn't end at Neptune or Pluto. It extended farther into a population of objects we had never known existed. And even the Kuiper Belt, vast as it is, turned out to be just one layer. Beyond it lies the scattered disk, where objects follow wildly elongated orbits. Beyond that, the Oort Cloud, a shell of debris so distant it's never been directly observed. Each discovery pushed the edge farther out. Each new layer revealed that the solar system is far larger, far more complex, and far more mysterious than anyone imagined. So here we are, on Earth, looking outward. We've learned that the planets occupy only a small inner zone, that beyond them lies a frontier filled with icy remnants, scattered bodies, and unseen populations. That the sun's influence reaches farther than any telescope can see. And we've learned something else, something humbling. For all our science and exploration, we still don't know exactly where the solar system ends. We've sent spacecraft across billions of miles. We've mapped thousands of objects. We've measured the solar wind and traced the pull of gravity. But the edge keeps moving. Every time we think we've found it, we discover something farther still. That's the setting for tonight's journey. A solar system that is far larger than the bright inner planets suggest. A domain that stretches outward in layers, each one fainter and more distant than the last. From Earth, the sun feels like everything, but step far enough away, and it becomes just another star. The warmth fades, the light dims, the gravity weakens, and somewhere in that fading, the solar system dissolves into the galaxy. Tonight, we're going to follow that dissolve. We're going to trace the sun's reach outward, layer by layer, until we find the place, or places, where its influence finally ends. Or perhaps, where it simply becomes something else. For most of human history, the solar system seemed knowable, small, contained. The ancient Greeks watched 5 wandering stars move against the fixed background of the cosmos. Mercury, Venus, Mars, Jupiter, Saturn. They plotted their paths, built models, tried to understand the patterns. For 2,000 years, those 5 planets, plus Earth, were the entire known solar system. Then came the telescope. In 1610, Galileo Galilei pointed his crude instrument at the night sky and saw moons orbiting Jupiter. The universe suddenly became larger, more complex. If Jupiter had moons, then the solar system wasn't just planets circling the sun. It was a hierarchy, worlds orbiting worlds. Over the next 2 centuries, astronomers discovered Uranus in 1781 and Neptune in 1846. Each discovery pushed the boundary outward. Each new world suggested that the solar system might be larger than anyone had thought. But Neptune felt like the end. It was so far away, 30 times Earth's distance from the Sun, that it took more than a century and a half to complete a single orbit. Its discovery had been a triumph of mathematics. Astronomers had noticed irregularities in Uranus's orbit, calculated where another planet must be, and found Neptune almost exactly where the equations predicted. After that, many assumed the search was over. 8 planets. A neat, orderly system. Nothing left to find. Then, in 1930, Clyde Tombaugh, a young astronomer working at Lowell Observatory in Arizona, discovered something unusual. A faint point of light moving slowly against the stars. Farther out than Neptune. Smaller. Stranger. They named it Pluto, after the Roman god of the underworld. For 76 years, it was celebrated as the 9th planet. Textbooks were rewritten. Children memorized a new list. The solar system had 9 planets, and Pluto marked the edge. But even as Pluto was being discovered, astronomers were beginning to suspect that it wasn't alone. As early as 1943, an Irish astronomer named Kenneth Edgeworth suggested that a belt of icy objects might exist beyond Neptune. In 1951, Dutch astronomer Gerard Kuiper made similar predictions. They reasoned that the disk of material from which the planets formed wouldn't simply end at Neptune. There should be debris, leftovers, a population of small bodies orbiting in the outer reaches. For decades, this remained theoretical. Telescopes weren't powerful enough to see objects so small and distant. The predicted belt, if it existed, was invisible. Then, in 1992, everything changed. Two astronomers, David Jewett and Jane Liu, working at the Mauna Kea Observatory in Hawaii, discovered a faint object beyond Neptune. They designated it 1992 QB1. It was small, perhaps 100 miles across, and it orbited at about 44 times Earth's distance from the Sun. One object could have been a fluke, but over the next few years they found more, and more. By the end of the decade, hundreds of objects had been discovered beyond Neptune. By the 2000s, thousands. The Kuiper Belt, as it came to be called, was real, and it was enormous. It stretched from about 30 astronomical units just beyond Neptune to 50 astronomical units or more. Within that span, astronomers estimated there might be hundreds of thousands of objects larger than 60 miles across, perhaps billions of smaller fragments, all of them icy remnants from the solar system's formation, preserved in deep freeze for 4.5 billion years. Pluto, it turned out, wasn't the 9th planet. It was simply the largest, or at least the first discovered, member of a vast population. It had neighbours, thousands of them. In 2005, astronomers discovered Eris, an object slightly smaller than Pluto in diameter but more massive. Then Haumea, an elongated world spinning so fast it had stretched into the shape of a football. Then Makemake, another icy dwarf covered in frozen methane. These discoveries forced a reckoning. If Pluto was a planet, then so were Eris, Haumea, and Makemake. And if those were planets, then dozens, maybe hundreds more, would have to be added to the list as telescopes improved. In 2006, the International Astronomical Union made a decision. They created a new category, dwarf planets. Pluto was reclassified. It was no longer the 9th planet, but the first dwarf planet, a founding member of a new class of objects that were large enough to be round but hadn't cleared their orbits of debris. The decision was controversial. Many people felt a deep connection to Pluto. It had been a planet for their entire lives. But scientifically, the reclassification made sense. Pluto belonged to a family, not standing alone at the edge but surrounded by kin, and the Kuiper Belt itself was only part of the story. Beyond the relatively organized belt lay the scattered disk, a region where objects followed wildly eccentric orbits, stretching hundreds of astronomical units from the Sun. One such object, Sedna, discovered in 2003, follows an orbit so extreme that its closest approach is 76 astronomical units, and its farthest point is nearly 1,000 astronomical units. One orbit takes more than 11,000 years. Sedna's orbit couldn't be explained by Neptune's gravity alone. It was too detached, too far away. Some astronomers suggested it had been nudged into place by a passing star billions of years ago. Others proposed the existence of a massive, undiscovered planet lurking in the outer solar system, a world 10 times the mass of Earth orbiting hundreds of astronomical units away. This hypothetical world, sometimes called Planet 9, remains unconfirmed, but the orbits of several distant objects seem to cluster in ways that suggest something massive is pulling on them. The search continues. Each discovery, each new population, pushed the boundary of the solar system farther out. The Kuiper Belt extended the edge to 50 astronomical units. The scattered disk stretched it to hundreds, and beyond that, astronomers theorized about the Oort Cloud, a vast spherical shell of comets that might extend a light year or more from the Sun. The solar system, once thought to end at Neptune, now appeared to reach almost halfway to the nearest star. This was the spark of mystery, not a single discovery, but a cascade of them, each one revealing that the solar system was larger, stranger, and more layered than anyone had imagined. And with each discovery came new questions. How did these objects get there? Were they leftovers from planet formation? Or had they been scattered outward by gravitational interactions? How many more were waiting to be found? And where, exactly, did the solar system end? The edge kept moving. Every time astronomers thought they had mapped the frontier, they found something beyond it. The solar system wasn't a fixed structure with clear boundaries. It was a gradient, a fading of influence that stretched farther than telescopes could see. For Clyde Tombaugh, the young astronomer who discovered Pluto in 1930, the solar system had 9 planets and ended at about 40 astronomical units. For astronomers working in the 1960s and 70s, the edge was still Neptune or Pluto, somewhere around 30 to 50 astronomical units. But for astronomers today, the answer is far more complicated. The edge is at 50 astronomical units if you measure by the Kuiper Belt, at 120 if you measure by the heliopause, at thousands if you measure by the scattered disk, at 100,000 or 2 light years if you measure by the Oort Cloud or the Sun's gravitational reach. The discovery that sparked this expansion wasn't a single moment. It was a slow unraveling, a realization that the solar system we thought we knew was only the bright inner core of something much, much larger. And that unraveling continues. New objects are discovered every year. New orbits are calculated. New theories are proposed. The map keeps expanding. Somewhere out there, beyond the reach of current telescopes, there may be objects we haven't dreamed of yet. Worlds orbiting in the darkness, taking millions of years to circle the Sun once. Remnants of the solar system's birth, preserved in conditions so cold that nothing has changed in billions of years. The spark of mystery, lit by that first object discovered beyond Neptune in 1992, continues to burn. It asks us to look farther, to question our assumptions, to accept that the solar system is not what we thought it was. It's larger, stranger, more beautiful, and still, after all our exploration, mostly unknown. The spark of mystery, lit by that first object discovered beyond Neptune in 1992, continues to burn. It asks us to look farther, to question our assumptions, to accept that the solar system is not what we thought it was. It's larger, stranger, more beautiful, and still, after all our exploration, mostly unknown. The edge we once drew with confidence has become a question mark, stretched across distances that challenge our ability to comprehend them. And that question mark invites us deeper, outward, into realms where the Sun's influence grows faint but never quite disappears. When the first objects beyond Neptune were confirmed in the early 1990s, the astronomical community responded with a mixture of excitement and disbelief. Some had predicted these discoveries. Gerard Kuiper, Kenneth Edgeworth, and others had suggested decades earlier that a belt of debris should exist beyond the planets. But predictions are one thing, seeing them confirmed is another. David Jewett and Jane Liu, the astronomers who discovered the first confirmed Kuiper Belt object in 1992, had spent years searching. They had photographed the same patches of sky night after night, comparing images to look for anything that moved. It was painstaking work, tedious. Most nights yielded nothing. Then, on August 30th, 1992, they found it, a faint dot moving slowly against the background stars. At first, they could hardly believe it. After years of searching, the object they had been looking for was finally there. They designated it 1992 QB1. Later, it was given the informal name Smiley, though it never received an official name. It was about 100 miles across, orbiting at 44 astronomical units from the Sun. Small, distant, faint, but real. When they announced the discovery, reactions were mixed. Some astronomers were thrilled. This was the confirmation of decades-old theories. It suggested that the solar system extended far beyond the 8 major planets, that there was a whole population of objects waiting to be discovered. Others were skeptical. One object wasn't enough to prove the existence of a belt. It could be an outlier, a fluke. Maybe it was a captured comet or a rogue object that had wandered in from elsewhere. But then came the second discovery, and the third. Within a few years, dozens of objects had been found. Within a decade, hundreds. The skepticism faded. The Kuiper Belt was real, and it was enormous. For the public, the discovery didn't immediately register. Pluto was still the 9th planet. The solar system, as far as most people knew, ended somewhere around Pluto's orbit. These new objects were too faint, too distant, too technical to capture widespread attention. But within the scientific community, something profound was happening. The solar system was being rewritten. Textbooks would need to be updated. Models of planetary formation would need to be revised. And the question of where the solar system ended, once thought to be settled, was suddenly wide open again. The discovery of Eris in 2005 brought the question into sharper focus. Eris was slightly smaller than Pluto in diameter, but more massive. It orbited much farther out, ranging from 38 to 97 astronomical units from the Sun. Its discovery forced astronomers to confront an uncomfortable truth. If Pluto was a planet, then Eris had to be one too. But if both were planets, then the list wouldn't stop there. More objects of similar size were being discovered. Haumea, Makemake, Quaoar, Sedna. The number of planets could grow into the dozens. Or Pluto wasn't a planet at all. It was simply the first member of a new class of objects, large enough to be round, but not large enough to dominate their orbits. The debate was intense. Astronomers gathered in Prague in August 2006 for a meeting of the International Astronomical Union. The question was simple but loaded. What is a planet? The answer they settled on created 3 criteria. A planet must orbit the Sun. It must be massive enough for gravity to pull it into a roughly spherical shape, and it must have cleared its orbital neighbourhood of other debris. Pluto met the first 2 criteria, but it failed the third. Its orbit was filled with other Kuiper Belt objects. By this definition, Pluto was not a planet. It was a dwarf planet, a new category that included Eris, Haumea, Makemake, and eventually others. The decision was announced on August 24, 2006. The solar system now had 8 planets. Pluto had been demoted. The public reaction was immediate and emotional. People felt a connection to Pluto. It had been part of the planetary family for 76 years. Many had grown up learning that the solar system had 9 planets. To lose Pluto felt like losing a friend. Petitions were launched. Debates erupted in schools and online forums. Some astronomers objected to the decision, arguing that the definition of clearing an orbit was arbitrary. Even Earth, they pointed out, shares its orbit with asteroids. Why should Pluto be held to a different standard? But for most scientists, the reclassification made sense. Pluto wasn't an oddball at the edge. It was part of a family. And recognizing that family, the Kuiper Belt, was more important than preserving Pluto's planetary status. The awe came from realizing how much we hadn't known. For a century and a half, astronomers had believed the solar system ended at Neptune. Then Pluto extended the edge slightly. But the discovery of the Kuiper Belt revealed that the outer solar system was far more populated, far more complex than anyone had imagined. Thousands of icy worlds, orbits that stretched hundreds of astronomical units, objects like Sedna that seemed to belong to a transitional zone between the Kuiper Belt and something even farther out. Each discovery added to the picture, showing that the solar system was layered, structured in ways that defied simple boundaries. The disbelief came from the scale. Even experienced astronomers had trouble grasping the distances involved. 50 astronomical units, 100, 1,000. These numbers were abstract, almost meaningless in human terms. Light from the sun takes 8 minutes to reach Earth. It takes more than 4 hours to reach Neptune. It takes nearly a day to reach the heliopause. And if the Oort Cloud exists as theorized, light takes weeks, even months, to reach its outer edge. Objects in the Kuiper Belt take hundreds of years to orbit the sun. Objects in the scattered disk take thousands. Objects in the Oort Cloud, if they exist, take millions. The timescales were as dizzying as the distances. For people trying to understand the solar system, the discoveries of the 1990s and 2000s created a cognitive shift. The bright inner planets, the ones we learn about in school, occupied only a tiny fraction of the sun's domain. Most of the solar system was dark, cold, and filled with objects we could barely see. This shift was both humbling and inspiring. Humbling because it showed how much we didn't know. Inspiring because it showed how much there was still to discover. Astronomers began to realize that the solar system wasn't a finished map. It was a frontier, and the edge of that frontier kept moving every time they looked deeper. The first response to these discoveries, then, was a mixture of emotions. Excitement at confirming theories, disbelief at the scale, frustration at having to redraw boundaries, and wonder at the complexity of the system we inhabit. For the scientists who spent their careers searching for these faint objects, the response was deeply personal. David Jewett later described the moment of discovering the first Kuiper Belt object as one of the most exciting of his life. After years of fruitless searching, the confirmation that the belt existed was profound. Jane Liu, his collaborator, spoke of the patience required, night after night of observation, most of them yielding nothing, but the persistence paid off, and their discovery opened the door for thousands more. Mike Brown, the astronomer who discovered Eris and several other large Kuiper Belt objects, titled his memoir, How I Killed Pluto and Why It Had It Coming. The title was playful, but it reflected the controversy his discoveries had sparked. By finding objects as large as Pluto, he had forced the question of what counted as a planet. The answer led to Pluto's reclassification. But Brown also spoke of the awe he felt looking at images of these distant worlds. Eris, Haumea, Make. Each one was a world in its own right, with its own story, its own surface features, its own history. They might not be planets by the new definition, but they were no less fascinating. The first response to the discovery of the outer solar system, then, was complex. It wasn't just awe or just disbelief. It was both. A recognition that the universe is larger and stranger than we expect, even when we think we understand it, and a reminder that every answer leads to new questions, every discovery to new mysteries, waiting just beyond the edge of what we can see. Science thrives on precision. It asks for definitions, measurements, clear boundaries. But the solar system, as it turns out, resists that precision. Ask a simple question: where does the solar system end? And you'll get not one answer, but many. Each one is scientifically valid. Each one is based on measurable phenomena, and yet they contradict each other, pointing to different edges separated by vast distances. This is the central contradiction at the heart of our journey tonight. The solar system doesn't have a single boundary. It has multiple boundaries, each defined by a different kind of influence. If you define the solar system by its planets, the edge is Neptune. The eighth planet orbits at an average distance of 30 astronomical units from the Sun. Beyond Neptune, there are no more large, spherical worlds sweeping through space in predictable orbits. The planetary system, by this definition, ends there. But this definition feels incomplete, because beyond Neptune, space is not empty. It's filled with smaller objects, dwarf planets, Kuiper Belt objects, scattered disk bodies. They may not be planets by the strict definition, but they orbit the Sun. They're part of the system, so why wouldn't they count toward the boundary? If you define the solar system by these icy populations, the edge moves outward. The Kuiper Belt extends to about 50 astronomical units. The scattered disk stretches even farther, with objects like Sedna reaching close to 1,000 astronomical units at their most distant point. But even this feels incomplete, because the scattered disk is not the outermost population. Beyond it, theorists predict the existence of the Oort Cloud, a vast spherical shell of comets surrounding the solar system. The Oort Cloud has never been directly observed. No telescope has ever seen one of its members in place, but the evidence for its existence is strong. Long-period comets, the ones that take thousands or millions of years to orbit the Sun, arrive from every direction in the sky, not just along the plane of the planets, but from above and below, from all angles. Their distribution suggests they come from a spherical reservoir, not a flat disk. That reservoir is the Oort Cloud. If the Oort Cloud exists, it extends from about 2,000 astronomical units to perhaps 100,000 astronomical units. That's nearly 2 light years from the Sun. By this definition, the solar system is almost halfway to the nearest star. So is the edge at 30 astronomical units, 50, 1,000, 100,000? Each answer is based on real observations, real physics. But they can't all be right as the edge. So which one is? The contradiction deepens when you consider other kinds of boundaries. The heliopause, the place where the solar wind stops and the interstellar medium takes over, lies at about 120 astronomical units. Voyager 1 crossed it in 2012. By that measure, the solar system ends there. But Voyager 1 is still orbiting the Sun. Its trajectory is still shaped by the Sun's gravity. So in another sense, it hasn't left the solar system at all. It's left the heliosphere, the bubble of solar wind, but it's still gravitationally bound. If you define the solar system by gravity, the boundary is much farther out. The Sun's gravity extends infinitely, in theory, growing weaker with distance, but never reaching zero. But at some point, the Sun's pull becomes weaker than the pull of the galaxy as a whole. That point, where the Sun's gravitational influence is overtaken by the Milky Way's, marks the outer limit of the Sun's Hill sphere. For the Sun, the Hill sphere is estimated to extend about 1 to 2 light years. Maybe more. By this measure, the solar system's true diameter could be 4 light years, almost the distance to Proxima Centauri, the nearest star. So now we have even more contradictions. The edge is at 30 astronomical units by planetary orbits, at 50 by the Kuiper Belt, at 120 by the heliopause, at thousands by the scattered disk, at 100,000 by the Oort Cloud, at 200,000 by the Hill sphere. Each definition is rooted in science. Each one measures something real, but they give wildly different answers. This is where mystery enters, because science, for all its precision, cannot provide a single, unified answer to the taxon question of where the solar system ends. The system itself defies singular definition. It's layered, overlapping, a set of nested zones, each one fading into the next. The contradiction reveals something profound about boundaries in general. We want them to be clear. We want lines on maps, edges we can point to and say, here it is. This is where one thing stops and another begins. But nature doesn't work that way. Not in space. Not in most places, really. Boundaries are human constructs. They're useful for organizing information, for teaching, for understanding. But they're not absolute truths. The solar system is a gradient. The sun's influence fades gradually with distance. Its light dims. Its heat weakens. Its gravity lessens. Its wind slows. Each kind of influence fades at a different rate, creating different boundaries. And those boundaries shift. The heliopause expands and contracts with the solar cycle. The Oort Cloud's inner edge may be disturbed by passing stars, sending comets inward or scattering them outward. The orbits of scattered disk objects change over millions of years as they interact with Neptune or feel the tidal pull of the galaxy. Nothing is fixed. The solar system is dynamic, breathing, evolving. Its edges are not walls but transitions. So when science offers multiple answers to the question of where the solar system ends, it's not because science has failed. It's because the question itself is more complex than it first appears. The solar system doesn't end in one place. It ends in many places, depending on what you're measuring. This contradiction between precision and ambiguity is central to understanding the solar system's true nature. We can measure distances with incredible accuracy. We can calculate orbits, track particles, map magnetic fields, but all that precision doesn't give us a single boundary. It gives us a set of boundaries, each one valid, each one incomplete on its own. And there's beauty in that, because it means the solar system is richer, more nuanced than any single definition could capture. It's not a box. It's not a sphere. It's an influence that spreads outward in layers, each one telling a different story about the sun's reach. For scientists, this contradiction is a challenge. How do you communicate the size of the solar system when there's no single answer? How do you teach it? How do you put it on a diagram? For philosophers, it's a reminder that categories are tools, not truths. The label, solar system, is useful. But nature doesn't care about our labels. It simply is. And for anyone lying awake at night, wondering about the edges of things, it's an invitation. An invitation to sit with ambiguity, to accept that some questions have multiple answers, all of them true in different ways. The solar system ends at Neptune, and it ends at the heliopause, and it ends at the Oort Cloud, and it ends nowhere, fading imperceptibly into the galaxy. All of these are true. None of them is complete. And in that incompleteness, there's mystery. Not the kind of mystery that frustrates, but the kind that opens. The kind that says, look deeper, think harder. Accept that the universe is more complex than any single story can hold. Science gives us tools to measure, but mystery reminds us that measurement is only one way of knowing. The solar system, in all its layered, contradictory vastness, asks us to hold both at once, precision and ambiguity, knowledge and wonder, science and mystery, not as opposites, but as partners in the same journey. And so the contradiction stands, not as a problem to be solved, but as a truth to be embraced. The solar system has many edges, and that multiplicity reveals something essential about the cosmos. It shows us that boundaries are not failures of understanding, but invitations to see more completely. Every measurement adds to the picture without completing it. Every definition illuminates one aspect while leaving others in shadow. And in accepting this, we move closer to the real nature of the system we inhabit, a place where nothing ends sharply and everything fades into everything else, where the line between solar and galactic, between here and there, is not a barrier but a gradient, a slow transformation that reflects the universe's fundamental continuity. When astronomers gathered to discuss the boundaries of the solar system, they brought with them not just data, but perspectives, different ways of seeing, different priorities for what matters most. And as is often the case in science, when perspectives differ, theories divide. Some astronomers argue that the solar system should be defined by its planetary orbits. This is the traditional view, the one taught in schools for generations. By this measure, the system ends at Neptune, 30 astronomical units from the Sun. Everything beyond that is post-planetary space, a realm of debris and dwarf worlds that don't count toward the system's true boundary. The logic is clean. Planets are the dominant objects, the ones massive enough to clear their orbital paths, the ones whose gravity shapes the structure of the system. If you're defining the solar system, you should define it by its most important members. But others push back. What about Pluto? What about Eris, Haumea, Makemake? These are substantial worlds, large enough to be round, geologically interesting, with atmospheres and moons. To dismiss them as mere debris feels arbitrary. Just because they haven't cleared their orbits doesn't mean they're not part of the system's architecture. By this second view, the solar system extends to include the Kuiper Belt and scattered disk, reaching 50 or even hundreds of astronomical units. The boundary isn't set by planets alone, but by all the objects born from the Sun's protoplanetary disk. A third group of astronomers focuses on the heliopause. This is the boundary crossed by Voyager 1 and Voyager 2, the place where the solar wind stops and interstellar space begins. It's a physical transition, measurable by instruments, a real change in environment. For these scientists, the heliopause is the most meaningful edge. It marks the end of the Sun's direct influence through particles and plasma. Beyond it, you're no longer inside the Sun's bubble. You're in the interstellar medium, the space between stars. By this definition, the solar system ends at about 120 astronomical units. It's a smaller boundary than the Oort Cloud, but it's based on something tangible. Voyager's instruments recorded the crossing. It's not theoretical, it's real. But a fourth group argues that the heliopause is too restrictive. Yes, the solar wind stops there, but the Sun's influence doesn't. Gravity extends far beyond the heliopause. So does light, however faint. To define the edge, by plasma alone ignores other kinds of influence that reach much farther. These astronomers point to the Oort Cloud. If it exists as predicted, it extends tens of thousands of astronomical units from the Sun, perhaps 100,000 or more. Objects in the Oort Cloud are still gravitationally bound to the Sun. They orbit it, however slowly. They belong to the system. By this measure, the solar system extends nearly 2 light-years, almost halfway to Proxima Centauri. It's a staggering distance, but it's based on the reach of the Sun's gravity, the most fundamental force binding the system together. Still others propose the Hill sphere as the ultimate boundary, The Hill sphere is the region where an object's gravity dominates over the tidal forces of a larger body it orbits. For the Sun, orbiting the centre of the Milky Way, the Hill sphere marks the limit of its gravitational control relative to the galaxy. Estimates place the Sun's Hill sphere at about 2 to 3 light-years in radius. Beyond that, the pull of the galaxy is stronger than the Sun's pull. Objects can't remain in stable orbits. They drift away, claimed by the Milky Way as a hole. This is the largest proposed boundary, the one that makes the solar system almost as wide as the distance to the nearest star. It's theoretical, not directly observable, but it's based on solid gravitational physics. So there are at least 5 competing theories for where the solar system ends. Each one is defended by scientists with good reasons. Each one highlights a different aspect of the system's structure. The divisions run deeper than just numbers. They reflect different philosophies about what the solar system fundamentally is. Is it a family of planets? Then Neptune marks the edge. Is it the collection of all objects born from the Sun's formation? Then the Kuiper Belt, or scattered disk, is the boundary. Is it the region dominated by the Sun's plasma output? Then the heliopause defines it. Is it the reach of the Sun's gravity over individual objects? Then the Oort Cloud marks the limit. Is it the region where the Sun's gravity controls motion relative to the galaxy? Then the Hill sphere is the answer. Each theory is internally consistent. Each makes sense from its own perspective. But they can't all be right if we're looking for a single edge. This is where minds divide, not just in astronomy, but in how we think about boundaries in general. Some people want clarity. They want definitions that are precise, unambiguous, useful for teaching and communication. For them, choosing one boundary, probably Neptune or the heliopause, makes sense. It gives a clear answer. Others embrace complexity. They argue that the solar system is inherently multi-layered, that trying to reduce it to a single boundary does violence to its true nature. For them, all 5 boundaries are valid. The system ends in different places depending on what you're measuring. The debate has practical implications. When space agencies plan missions, when educators write textbooks, when science communicators explain the solar system to the public, they have to choose. They have to say, the solar system extends this far, and whatever choice they make, they're implicitly taking a side in the theoretical debate. Most choose the heliopause for practical purposes. It's measurable, reached by spacecraft, and larger than the planetary system but smaller than the vast theoretical constructs of the Oort Cloud or Hill sphere. It's a compromise, but the compromise doesn't satisfy everyone. Some scientists continue to argue for the Oort Cloud, insisting that gravitationally bound objects must count. Others defend the planetary boundary, saying that's what most people mean when they talk about the solar system. Neptune marked the edge. Then Pluto was discovered, and the edge moved slightly. Then the Kuiper Belt was found, and the edge moved much farther. Then Voyager crossed the heliopause, adding another layer. Now the Oort Cloud and Hill sphere push the theoretical boundary to light years. Each generation of astronomers inherits a slightly different map, and each generation revises it based on new data. The theories divide not because scientists can't agree, but because the question itself keeps expanding as knowledge deepens. There's also a personal element. Astronomers who spend their careers studying the Kuiper Belt naturally see it as central to the solar system's definition. Those who study the solar wind emphasize the heliopause. Those who model long-period comets point to the Oort Cloud. Everyone's perspective is shaped by what they study most closely. This doesn't make any view less valid. It just means that the question of boundaries is not purely objective. It's influenced by focus, by priorities, by what aspects of the system you find most meaningful. In the end, the theories divide because the solar system is larger and more complex than any single theory can capture. It's a structure with multiple edges, each one real, each one important. For those of us listening tonight, trying to understand where the solar system ends, the divided theories offer a kind of freedom. We don't have to choose. We can hold all the answers at once. Neptune and the heliopause and the Oort Cloud. All of them true, all of them incomplete. The solar system ends where the planets stop, and where the solar wind stops, and where gravity stops dominating. All of these are edges. All of these matter. And in recognizing that, we see the system not as a simple object, but as a layered, living structure that defies singular definition. The minds divide not because the question is unanswerable, but because it has too many answers. And perhaps that's the most honest conclusion. The solar system doesn't end in one place. It ends in many. And each ending is a doorway to a different understanding of what the sun's domain truly means. The theories will continue to divide as new discoveries emerge. Perhaps Planet 9 will be found, reshaping our understanding of the scattered disk. Perhaps the first direct observation of an Oort Cloud object will confirm its existence beyond doubt. Perhaps future spacecraft will travel far enough to measure the transition into galactic dominance firsthand. Each new piece of evidence will add weight to one theory or another, or perhaps create entirely new ones, but the fundamental truth will remain. The solar system is not a single thing with a single edge, but a cascade of influences fading into the larger universe. And our theories, divided as they are, simply reflect different ways of measuring that fade. If you want to understand where something ends, sometimes the only way is to go there, to cross the boundary yourself and measure what changes. That's exactly what humanity decided to do. Not in person, not yet, but through machines, through spacecraft built to travel farther than any object we'd ever sent into the void. The story begins in the 1970s during a rare alignment of the outer planets. Jupiter, Saturn, Uranus, and Neptune would arrange themselves in such a way that a spacecraft could visit all four, using each planet's gravity to slingshot to the next. The opportunity wouldn't come again for 176 years. NASA seized it. They designed two spacecraft, twins, built with identical instruments and identical missions. They named them Voyager 1 and Voyager 2. The missions launched in 1977. Voyager 2 went first, on August 20th. Voyager 1 followed on September 5th, taking a faster trajectory that would allow it to overtake its twin. Both spacecraft were small, about the size of a compact car. They carried cameras, spectrometers, magnetometers, particle detectors, everything needed to study the giant planets up close. They were powered not by solar panels, which would be useless so far from the sun, but by radioisotope thermoelectric generators, small nuclear batteries that converted heat from decaying plutonium into electricity. The power output was modest, about 470 watts at launch, roughly the same as a household refrigerator, and it would decline over time as the plutonium decayed. Engineers knew the spacecraft had limited lifespans. Eventually, the power would drop too low to operate the instruments, and the Voyagers would fall silent. But in 1977, that felt like a distant problem. The immediate goal was Jupiter and Saturn. Anything beyond that was a bonus. Voyager 1 reached Jupiter in March 1979. The images it sent back were astonishing. The Great Red Spot, a storm larger than Earth, swirled in intricate detail. Lightning flickered in the atmosphere. Auroras glowed near the poles. And the moons. O. The moons. Io, the innermost large moon, was covered in active volcanoes. Plumes of sulfur dioxide erupted hundreds of miles above the surface. It was the first time active volcanism had been seen beyond Earth. Europa, the next moon out, was covered in smooth ice crisscrossed with cracks. Beneath that ice, scientists suspected might be a liquid ocean. Ganymede and Callisto, the outer moons, revealed ancient, cratered surfaces with hints of geological activity long ago. Each moon was a world unto itself, complex and strange. Voyager 2 followed 4 months later, in July, confirming and expanding on its twins' discoveries. Then, both spacecraft continued to Saturn. At Saturn, Voyager 1 arrived in November 1980. It revealed the ring system in unprecedented detail. Thousands of ringlets, some braided, some kinked, all shaped by the gravity of tiny shepherd moons. The largest moon, Titan, appeared as a hazy orange sphere, its thick atmosphere hiding the surface below. Voyager 2 reached Saturn in August 1981. After its Saturn encounter, Voyager 1's trajectory took it upward, out of the plane of the planets, on a path toward interstellar space. But Voyager 2 continued onward to Uranus and Neptune, the only spacecraft ever to visit those distant worlds. At Uranus, in January 1986, Voyager 2 found a bland blue-green planet, tilted so far on its side that it essentially rolled along its orbit. Its moons, though, were fascinating. Miranda, in particular, showed a surface that looked like it had been shattered and reassembled, with cliffs, valleys, and strange geometric patterns. At Neptune, in August 1989, Voyager 2 revealed a dynamic atmosphere with the fastest winds in the solar system and a large dark storm. Triton, Neptune's largest moon, had geysers of nitrogen erupting from beneath its frozen surface. With Neptune, the grand tour was complete. Both Voyagers had fulfilled their primary missions. They had visited the giant planets, sent back thousands of images, transformed our understanding of the outer solar system, but they were still functioning, still transmitting, still travelling outward at tens of thousands of miles per hour. And so NASA extended their missions again, rebranding them as the Voyager Interstellar mission. The new goal was to reach the heliopause, the boundary where the solar wind stops. No one knew exactly how far away it was. Estimates ranged from 80 to 150 astronomical units. It could take decades to get there. As the Voyagers travelled outward, they measured the solar wind, tracking its density and speed. They measured cosmic rays, high-energy particles from beyond the solar system. They measured magnetic fields, watching for changes that would signal the approach of the boundary. The journey was slow. 10 astronomical units per decade. 20. 30. The spacecraft were moving faster than any human-made objects before them. But space is so vast that even at those speeds, progress felt glacial. In 1990, Voyager 1 turned its camera back toward the inner solar system and took a final set of images. A family portrait of the planets. From 4 billion miles away, Earth appeared as a tiny pale blue dot, barely a pixel across, suspended in a beam of scattered sunlight. Carl Sagan, the astronomer and science communicator, later wrote about that image. He called Earth a mote of dust suspended in a sunbeam, a lonely speck in the great enveloping cosmic dark. The image became iconic, a reminder of how small we are, how fragile, how precious. After that, the cameras were turned off to save power. From that point forward, the Voyagers were blind, their instruments focused on particles and fields rather than images. The years passed. The 1990s became the 2000s. The voyagers continued outward, still transmitting, still measuring. Engineers continued to monitor them, adjusting systems, shutting down instruments one by one as power declined. In 2004, Voyager 1 crossed a region called the termination shock, where the solar wind begins to slow as it encounters the pressure of the interstellar medium. The crossing was marked by changes in particle density and magnetic field orientation. It meant the heliopause was getting close, but it took 8 more years. 8 years of waiting, of incremental measurements, of watching for the signs. Then, in August 2012, Voyager 1's instruments detected a sudden change. The count of solar particles dropped. The count of galactic cosmic rays surged. The spacecraft had crossed the heliopause. It was no longer inside the heliosphere. It was in interstellar space. The announcement came a year later, in September 2013, after scientists had confirmed the data. Voyager 1 had travelled 11 billion miles, more than 120 astronomical units, farther than any human-made object in history, and it had crossed a boundary that, until that moment, was purely theoretical. Voyager 2 followed in November 2018, crossing the heliopause at a slightly different location, about 119 astronomical units from the Sun. Its instruments, more functional than Voyager 1's, provided additional data about the transition. Both spacecraft are still out there, still transmitting faint signals back to Earth. The signals take more than 21 hours to travel from Voyager 1, and the delay grows longer every day. The power continues to decline. Sometime in the 2020s or early 2030s, the Voyagers will finally fall silent, but even then, they'll continue to drift. In about 40,000 years, Voyager 1 will pass within about 1.6 light-years of a star called Gliese 445. In about 300,000 years, Voyager 2 will pass within a similar distance of another star. By then, human civilization will be unimaginably different, or perhaps gone. But the Voyagers will continue, silent and eternal, carrying with them the golden records, messages from Earth, greetings in dozens of languages, sounds and images of our world, sent into the cosmos as a declaration that we were here. The investigation, the pursuit of the solar system's edge, succeeded. The Voyagers reached the heliopause and confirmed its existence. They measured the transition from solar to interstellar space. They gave us our first direct data about what lies beyond the Sun's bubble. But in doing so, they also revealed how much farther the solar system extends. Beyond the heliopause, the Sun's gravity still holds sway. The Voyagers are still in orbit, still part of the system. They've crossed one boundary, but not others. The pursuit continues even as the spacecraft falls silent. New missions are being planned. New telescopes are scanning the outer reaches. New theories are being tested. The investigation that began with 2 spacecraft launched in 1977 is far from over, because every answer leads to new questions. Every boundary crossed reveals another boundary beyond. The solar system, as the Voyagers showed us, is larger than we thought, and the true edge, if there even is one, still lies ahead, waiting to be reached. Science is built on data, not speculation, not guesswork, but measurements, numbers, patterns observed and recorded with precision. The question of where the solar system ends, for all its philosophical complexity, ultimately comes down to data. What can we measure? What changes as we move outward? What clues and fragments tell us we've crossed a boundary? The Voyager spacecraft provided the first direct measurements of the heliopause, but the data they collected was subtle, requiring careful analysis to interpret. In the years leading up to the heliopause crossing, Voyager 1's instruments tracked several key quantities: the density of solar wind particles, the intensity of cosmic rays from beyond the solar system, the strength and direction of magnetic fields. Each measurement provided a piece of the puzzle. The solar wind, near Earth, consists of about 5 to 10 particles per cubic centimetre, electrons and protons streaming from the Sun at speeds of 300 to 800 kilometers per second. It's tenuous by earthly standards, thinner than the best vacuum we can create in a laboratory, but it's measurable, and it carries energy and momentum. As Voyager 1 travelled outward, the solar wind density didn't decrease smoothly. It varied with the solar cycle, with transient events like coronal mass ejections, with distance from the Sun. But overall, the trend was downward. Fewer particles per cubic centimetre the farther out you went. In 2004, at about 94 astronomical units, Voyager 1 crossed the termination shock. This is the place where the solar wind, encountering the pressure of the interstellar medium, suddenly slows from supersonic to subsonic speeds. The crossing was marked by a sharp increase in particle density as the wind piled up, and by changes in the magnetic field. Beyond the termination shock, Voyager 1 entered a region called the heliosheath. Here, the solar wind is still present but slowed and turbulent, pushed back by the interstellar medium. The heliosheath extends from the termination shock to the heliopause, a distance of about 25 astronomical units. For 8 years, Voyager 1 travelled through the heliosheath, collecting data. The instruments showed that this region is complex, with layers, fluctuations, and interactions between solar and interstellar particles. It's not a smooth transition, but a messy one, a zone where two different plasma environments collide and mix. Then, starting in mid-2012, the instruments detected something different. The count of solar particles began to drop rapidly. At the same time, the count of galactic cosmic rays began to rise. These cosmic rays, high-energy protons, and atomic nuclei from supernova and other astrophysical sources, are blocked by the solar wind inside the heliosphere. But beyond the heliopause, they dominate. On August 25th, 2012, the transition was complete. Solar wind particles dropped to near zero. Cosmic rays reached a plateau. Voyager 1 had crossed the heliopause. Interestingly, the magnetic field didn't change direction as expected. Scientists had predicted that the interstellar magnetic field would point in a different direction than the heliosphere's field. But Voyager's magnetometer showed the field direction remained roughly the same, even as other measurements confirmed the crossing. This was puzzling. It suggested the boundary region is more complex than simple models predicted. Perhaps the interstellar magnetic field and the heliosphere's field are aligned by chance in this region. Or perhaps there are layers and structures at the heliopause that we don't yet understand. Voyager 2's crossing, 6 years later in November 2018, provided additional data. Its plasma instrument, which had failed on Voyager 1 decades earlier, was still functioning. It directly measured the plasma density and confirmed that Voyager 2 had indeed entered a different environment. The data from Voyager 2 also showed that the heliopause is not perfectly spherical. The two spacecraft crossed at different distances, 121 astronomical units for Voyager 1 and 119 for Voyager 2, suggesting the boundary ripples and flexes in response to solar activity and interstellar conditions. Beyond the spacecraft, astronomers have gathered other types of data to probe the solar system's extent. Observations of the Kuiper Belt have catalogued thousands of objects. By tracking their orbits, astronomers can map the structure of the belt, identifying different populations and resonances. The data shows the belt is not uniform but organized, with gaps and clusters shaped by Neptune's gravity. One particularly interesting piece of data comes from the clustering of orbits in the scattered disk. Several objects, including Sedna, have orbits that seem to align in a particular direction. The statistical significance of this clustering is debated, but if real, it could indicate the presence of an unseen massive planet, Planet 9. Shepherding these orbits, attempts to find Planet 9 have involved analysing data from sky surveys, looking for faint, slow-moving points of light that could be a distant planet. So far, no confirmed detection has been made, but the search continues, guided by models that predict where such a planet might be. Data about the Oort Cloud is indirect. We've never seen an Oort Cloud object in its home orbit, but by tracking long-period comets as they enter the inner solar system, astronomers can work backward, calculating where they came from. The data shows that these comets arrive from all directions, consistent with a spherical distribution. Their orbits have extremely long periods, millions of years in some cases, and very large semi-major axes. This supports the existence of a vast reservoir surrounding the solar system. Jan Oort, the Dutch astronomer who proposed the cloud's existence in 1950, based his theory on data about comet orbits. He noticed that many long-period comets have orbits with aphelia, their farthest points from the Sun, clustered around 50,000 astronomical units. This suggested a population at that distance, occasionally nudged inward by passing stars or galactic tides. Modern data has refined these estimates, but the basic picture remains. The Oort Cloud, if it exists, is the source of long-period comets, a spherical shell extending from thousands to tens of thousands of astronomical units. Another type of data comes from studying the Sun's motion through the galaxy. The Sun orbits the center of the Milky Way once every 230 million years. Along the way, it passes through regions of different density, encountering molecular clouds, spiral arms, and neighboring stars. Each encounter can disturb the Oort Cloud, sending showers of comets inward. By studying the timing of impacts on Earth and correlating them with the Sun's position in the galaxy, some scientists have proposed links between galactic environment and comet activity. The data is tantalizing but not conclusive. Data about the Sun's Hill sphere, the region where its gravity dominates over the galaxies, is purely theoretical. It's based on calculations rather than direct measurements. But those calculations are grounded in well-understood gravitational physics. The Hill sphere's radius depends on the Sun's mass, its distance from the galactic center, and the distribution of mass in the galaxy. Current estimates place the Hill sphere at about 2 to 3 light years, but the exact value is uncertain. It's a fuzzy boundary, not a sharp one, and it changes slightly as the Sun moves through different regions of the galaxy. All of this data, from Voyager's particle counts to comet orbits to gravitational models, builds a picture of the solar system's extent. Each piece of data is a fragment, a clue. No single measurement tells the whole story, but together they reveal a structure far larger than the bright inner planets suggest. The data shows that the solar system is layered. The planets occupy the innermost zone. The Kuiper Belt extends the structure farther. The scattered disk pushes into the thousands of astronomical units. The heliopause marks the end of the solar wind at about 120 astronomical units. The Oort Cloud, if real, extends tens of thousands of astronomical units, and the Hill sphere stretches to light years. Each layer is supported by data. Each one is measurable, or at least inferable from observations. The clues and fragments, when assembled, create a map of the Sun's domain that is far more complex than any simple boundary could capture. For scientists, the data is what makes the question of the solar system's edge answerable. Not with a single number, but with a set of numbers, each one tied to a specific kind of influence. The data turns philosophical questions into physical ones, abstract boundaries into measurable transitions, and the data continues to accumulate. New telescopes discover new objects, new missions send back new measurements, new models refine our understanding of gravity and plasma and orbital dynamics. With each new piece of data, the picture becomes clearer, richer, more detailed, but clarity doesn't always mean simplicity. The data has shown us that the solar system is vast, layered, and dynamic. It doesn't end in one place. It ends in many, and each ending is marked by its own set of clues and fragments, waiting to be measured and understood. Beneath every answer lies another question. Every discovery reveals something unexpected, hiding just beyond the edge of what we thought we knew. The solar system is no exception. As astronomers pushed their observations farther, as spacecraft traveled deeper into the outer reaches, a pattern emerged. The deeper they looked, the stranger things became. Beyond Neptune, beyond the Kuiper Belt, in the realm of the scattered disk, objects appeared that defied easy explanation. Their orbits were too elongated, too distant, too perfectly aligned to be random. Sedna was the first hint. Discovered in 2003, it orbits between 76 and nearly 1,000 astronomical units from the Sun. Its orbit takes more than 11,000 years to complete. And most puzzling of all, it's perihelion. Its closest approach to the Sun is far beyond Neptune's reach. Neptune's gravity couldn't have placed Sedna there. So, what did? Some astronomers suggested a passing star, billions of years ago, when the Sun was still in its birth cluster. A close encounter could have tugged Sedna outward, stretching its orbit without ejecting it entirely from the solar system. Others proposed a different explanation. Perhaps Sedna was nudged into place by a massive planet, as yet undiscovered, lurking in the outer solar system. At first, the planet idea seemed far-fetched. After all, if there were another planet out there, surely we would have seen it by now. We've mapped the sky. We've discovered thousands of Kuiper Belt objects. How could a planet remain hidden? But the outer solar system is vast. A planet at several hundred astronomical units would be incredibly faint. Reflecting only a tiny amount of sunlight, it would move slowly against the background stars, taking centuries to complete a single orbit. And if its orbit carried it through regions of the sky that haven't been surveyed thoroughly, it could remain undetected even in modern telescopes. Then, in the years following Sedna's discovery, more objects were found with similarly strange orbits. 2012 VP 113, another distant object with a perihelion beyond Neptune. 2013 RF 98, with an orbit that reaches beyond 1,000 astronomical units, and several others. What caught astronomers' attention was not just that these objects existed, but that their orbits seemed to cluster. Their perihelia pointed in similar directions. Their orbital planes tilted at similar angles. The clustering could be a coincidence. With a small sample size, patterns can emerge by chance. But it was also possible that something was shaping these orbits. Something massive. Something unseen. In 2016, two astronomers, Konstantin Batygin and Mike Brown, published a paper arguing that the clustering could be explained by a ninth planet. Not Pluto, which had been reclassified as a dwarf planet, but a new, massive world orbiting far beyond Neptune. They called it Planet 9, and their models suggested it could be about 10 times the mass of Earth. orbiting at an average distance of 400 to 800 astronomical units from the Sun. Its orbit would be highly elongated, taking 10 to 20,000 years to complete. If Planet 9 exists, it would be a genuine giant, larger than any of the terrestrial planets, smaller than the ice giants. It would dwarf Pluto, Eris, and all the other dwarf planets combined. And it would rewrite the solar system's architecture, adding a fifth giant planet to the four we already know. The evidence for Planet 9 is indirect. No one has seen it. No telescope has captured its light. But the gravitational fingerprints it would leave on other objects' orbits match what astronomers observe. Critics point out that the sample size is small. Only a handful of objects show the clustering, and observational bias could account for the pattern. Telescopes tend to survey certain regions of the sky more thoroughly than others, which could create an illusion of clustering where none exists. Proponents counter that the alignment is too strong to be purely coincidental. Computer simulations show that a massive planet in the outer solar system would naturally shepherd distant objects into clustered orbits exactly as observed. The debate continues. Searches for Planet 9 are ongoing, using powerful telescopes to scan the sky for faint, slow-moving objects. If it exists, it will eventually be found. If it doesn't, then astronomers will need another explanation for the orbital clustering. But Planet 9 is only one hidden truth lurking in the outer solar system. The scattered disk itself raises questions. How did so many objects end up on such extreme orbits? Neptune's gravity can scatter objects outward, but not all the way to Sedna's distance. Something else must have been involved. One possibility is that the early solar system was more chaotic than we thought. The giant planets may have migrated, shifting positions over millions of years. Jupiter may have moved inward while Neptune moved outward. This migration would have scattered countless icy bodies, flinging some into the scattered disk, others into the Oort Cloud, and still others into interstellar space. Computer models of planetary migration, called the NICE, model after the French city where it was developed, show that this scenario is plausible. It explains not just the scattered disk, but many other features of the solar system. The late heavy bombardment, a period about 3.9 billion years ago, when the inner planets were pummeled by impacts, could have been triggered by planetary migration stirring up the outer solar system. But even the NICE model doesn't explain everything. Some scattered disk objects, like Sedna, are too detached to be accounted for by planetary migration alone. Their orbits require additional explanations, such as passing stars or Planet 9. Another hidden truth involves the Oort Cloud itself. If it exists, it contains trillions of icy bodies, but we've never seen one directly. Every piece of evidence is indirect, inferred from comets that fall inward. How did the Oort Cloud form? The leading theory is that icy planetesimals, left over from planet formation, were scattered outward by the giant planets. Some were ejected entirely, escaping the solar system. Others settled into distant orbits, forming the Oort Cloud. But recent models suggest the process may have been more complex. The Oort Cloud may contain material not just from our solar system, but from neighbouring stars in the Sun's birth cluster. During close encounters, stars can exchange material, capturing each other's comets. If true, then the Oort Cloud is not purely solar in origin. It's partly galactic, a mixture of material from multiple stars. This raises profound questions. Are there objects in the Oort Cloud that formed around other stars? Are there compositions, isotope ratios, or structures that don't match the rest of the solar system? If we could study Oort Cloud objects directly, what would they tell us about the Sun's early environment? Another hidden truth concerns the heliopause itself. Voyager's crossing revealed that the boundary is more complex than expected. The magnetic field didn't flip direction as predicted. The transition was gradual rather than sharp, and the distance to the heliopause varies depending on the solar cycle and interstellar conditions. What does this complexity mean? Are there layers within the heliopause, regions where solar and interstellar plasma mix? Are there waves, ripples, structures that change over time? Voyager provided our first direct measurements, but 2 data points are not enough to fully map the boundary. Future missions will be needed to understand the heliopause in detail. And then there's the question of what lies beyond. Voyager is now in interstellar space, but it's still orbiting the Sun. It's still part of the solar system by some definitions. What does interstellar space look like farther out? How does the environment change as you move away from the heliopause? Are there gradients, boundaries, transitions we haven't yet imagined? The deeper mystery, the hidden truth beneath all these questions, revealing itself. Every layer we peel back exposes another. Every boundary we cross leads to new territory. The outer solar system is not a dead, empty expanse. It's a frontier, filled with objects and structures and phenomena we're only beginning to understand. Planet 9, if it exists, is the most dramatic possibility. A hidden giant, waiting to be discovered, lurking in the shadows. But even if Planet 9 turns out to be a mirage, the scattered disk, the Oort Cloud, the heliopause, and the interstellar medium beyond will continue to surprise us. Because the truth is, we're still in the early stages of exploring the solar system's edge. We've sent 2 spacecraft across the heliopause. We've discovered thousands of Kuiper Belt objects. We've inferred the existence of the Oort Cloud, but we haven't seen most of it directly. We haven't visited the scattered disk. We haven't captured an Oort Cloud object. We haven't mapped Planet 9's orbit if it exists. The hidden truth is that the solar system is larger, stranger, and more mysterious than we can fully grasp. And that mystery is not a failing. It's an invitation to keep looking, keep searching, keep pushing the boundaries of what we know. Somewhere out there, in the darkness beyond Neptune, the solar system is still unfolding its secrets. And we've only just begun to listen. There are moments in science when everything changes, not gradually, but suddenly. A single observation, a single crossing, and the world looks different afterward. August 25th, 2012 was one of those moments. On that day, more than 11 billion miles from Earth, Voyager 1 crossed an invisible line. Its instruments recorded a sudden change in the particles flowing past it. The solar wind, the stream of charged particles from the sun that had surrounded the spacecraft for 35 years, vanished. In its place, galactic cosmic rays flooded in, particles from supernovas and distant stars, no longer blocked by the sun's bubble. Voyager 1 had crossed the heliopause. It had left the heliosphere and entered interstellar space. The announcement didn't come immediately. Scientists needed time to analyze the data, to rule out other explanations, to be sure. For months, they debated. Was this really the heliopause, or just a temporary fluctuation in the solar wind? The magnetic field was the sticking point. Models predicted that beyond the heliopause, the direction of the magnetic field would change, rotating to align with the interstellar field. But Voyager's magnetometer showed no such rotation. The field direction stayed roughly the same, even as particle counts indicated a crossing. It was puzzling, but in September 2013, after more than a year of analysis, NASA held a press conference. They announced that Voyager 1 had indeed crossed the heliopause, becoming the first human-made object to enter interstellar space. The crossing had occurred in August 2012. the news resonated far beyond the scientific community. Headlines around the world proclaimed that humanity had left the solar system. Voyager 1, a machine built with 1970s technology, carrying messages from a world decades younger, had crossed a threshold no one had crossed before. But the announcement also sparked debate, because Voyager 1, while beyond the heliopause, was still orbiting the Sun. It was still bound by the Sun's gravity. It would remain so for tens of thousands of years, perhaps longer. So in one sense, it had left the solar system. In another, it never would. This paradox crystallized the question we've been exploring all night. What does it mean to leave the solar system? What does it mean for the solar system to end? Before Voyager's crossing, the question was theoretical. Scientists debated definitions, proposed boundaries, argued about where to draw the line. But it was all abstract. No one had actually reached any of the proposed edges. Voyager changed that. It reached the heliopause. It measured the transition. It sent back data showing that the heliopause is real, measurable, a physical boundary where one environment gives way to another. And in doing so, it forced a paradigm shift, a change in how we think about the solar system's edge. Before Voyager, many people thought of the solar system as ending at the planets. Neptune was the edge, or maybe Pluto. Everything beyond was vaguely defined, part of the solar system in name only. After Voyager, that view became untenable. The heliopause, at 120 astronomical units, is far beyond the planets. It's a real boundary, confirmed by direct measurement. But it's not the only boundary. The Sun's gravity extends much farther. The Oort Cloud, if it exists, stretches thousands of times farther still. Voyager's crossing showed that the solar system has multiple edges, not just one. It's a layered structure. And which edge you care about depends on what you're measuring. This realization was the paradigm shift. The solar system isn't a simple sphere with a single boundary. It's a complex, overlapping set of zones. Light fades at one distance. The solar wind stops at another. Gravity dominates to yet another. Each zone has its own edge, and all of them are part of the solar system's structure. For scientists, the shift was both liberating and challenging. Liberating because it meant they could stop arguing about which single boundary was correct. All of them were correct, in different ways. Challenging because it meant teaching and communicating the solar system's size became more complicated. There was no longer a simple answer to the question, how far does the solar system reach? For the public, the shift was subtler. Most people still think of the solar system as the Sun and its planets. News that Voyager crossed into interstellar space was exciting, but it didn't fundamentally change how they pictured the system. The planets are still the main characters in that story. But for those paying close attention, Voyager's crossing was profound. It showed that the space between the stars is not some distant, unreachable realm. It's right there, just beyond the heliopause. Voyager is already there, transmitting signals, still operating after more than 4 decades. The paradigm shift also changed how we think about exploration. Before Voyager, interstellar space felt impossibly far away. Now, we know it's reachable. Not easily, not quickly, but reachable. With 1970s technology, we reached the heliopause in 35 years. With better technology, future missions could reach it faster, study it more thoroughly, push even farther beyond. Voyager 2's crossing in 2018 reinforced the shift. It confirmed that the heliopause is real, that it surrounds the solar system, that it marks a genuine transition. The 2 spacecraft crossed at slightly different distances, showing that the boundary flexes and moves. But both crossings were unmistakable. The data from both voyages also revealed that the heliopause is more complex than simple models suggested. The magnetic field doesn't flip direction. The transition is gradual, with layers and fluctuations. The boundary is not a sharp wall but a zone, a region where solar and interstellar influences mix and compete. This complexity is itself part of the paradigm shift. We used to think of boundaries as clean lines on a map. The heliopause showed us that real boundaries are messy, dynamic, responsive to changing conditions. The solar system doesn't end sharply. It transitions, fades, blends. The turning point, then, was not just a single day in August 2012. It was a process, a gradual realization that the solar system is larger and stranger than we thought. Voyager's crossing was the catalyst, the moment that forced us to confront the complexity we had been avoiding, and it continues to unfold. Every year, Voyager 1 and 2 travel farther into interstellar space. Every year, they send back more data about what that space is like. Every year, our understanding deepens. Future spacecraft, if we build them, will follow in Voyager's path. They'll cross the heliopause, explore the interstellar medium, perhaps even reach the Oort Cloud. Each mission will add to the paradigm shift, showing us more of the structure, more of the layers, more of the boundaries we haven't yet imagined. The turning point was the moment we stopped asking where the solar system ends and started asking how it ends. Not with a single line, but with many. Not abruptly, but gradually. Not in one place, but across light years of space. Voyager's crossing was the moment that truth became undeniable. And in that moment, the solar system transformed from a tidy collection of planets into a vast, layered, dynamic structure stretching farther than most people ever imagined. The paradigm shift was not a revolution, it was an awakening, a realization that the universe is more complex than our categories allow, that boundaries are human inventions imposed on a reality that flows and fades. Voyager showed us that, and in showing us, it changed forever how we see our place in the cosmos. The paradigm shift continues today, not as a completed transformation, but as an ongoing process of discovery and realization. Each new mission planned, each distant object found, each model refined, adds another layer to our understanding. We now know that asking where the solar system ends is like asking where a sunset ends. There's no single moment when day becomes night, only a gradual fading through twilight, through dusk, through deepening darkness. The solar system fades the same way, layer by layer, influence by influence, until finally the sun is just another star, and we're no longer asking where its domain ends, but marveling that it ever seemed to have clear boundaries at all. That is the turning point's deepest lesson. Not where things end, but how. They transform. Every action creates ripples. Voyager's crossing of the heliopause sent ripples through the scientific community, through space agencies, through the way we think about exploration itself. The immediate consequence was excitement. For the first time, humanity had a foothold beyond the sun's bubble. We were no longer confined to the heliosphere. We had extended our reach, however slightly, into the space between stars. But excitement was tempered by reality. Voyager 1, while in interstellar space by one definition, was still bound to the sun. It would never escape the solar system's gravitational pull, not in any human timescale. It had crossed one boundary but remained inside others. This created a communication challenge. How do you explain to the public that Voyager has both left and not left the solar system? How do you convey the layered nature of boundaries without confusing people? NASA chose to emphasize the heliopause crossing. They described it as entering interstellar space, which was technically accurate. The environment Voyager 1 was experiencing was interstellar, not solar. But they also acknowledged that the sun's gravity still held the spacecraft, that it was still part of the solar system in that sense. The media coverage varied. Some outlets ran with headlines like "Voyager leaves the solar system," which was true from one perspective. Others ran with "Voyager enters interstellar space," which was more precise. A few dug deeper, explaining the multiple boundaries and the complexity of the question. For scientists, the crossing had immediate practical consequences. It validated decades of theoretical work. Models of the heliosphere, the solar wind, and the heliopause had predicted roughly where the boundary would be. Voyager's measurements confirmed those predictions, give or take a few astronomical units. But the data also raised new questions. Why didn't the magnetic field change direction? Why was the transition gradual rather than sharp? What was the structure of the region between the termination shock and the heliopause? These questions sparked new research. Scientists revisited their models, incorporating Voyager's data to refine their understanding. They realized that the heliopause is not a simple interface, but a complex boundary layer with mixing, turbulence, and reconnection of magnetic field lines. The crossing also had consequences for future mission planning. NASA and other space agencies began to consider seriously the idea of dedicated interstellar missions. Not just flybys, like Voyager, but spacecraft specifically designed to study the heliopause and the interstellar medium beyond. One proposal, called the Interstellar Probe, would travel faster than Voyager, reaching the heliopause in less than 20 years. It would carry modern instruments, far more capable than Voyager's, designed to study the transition in detail. It would be powered by advanced propulsion, possibly a solar sail, or nuclear electric propulsion, allowing it to reach speeds of tens of astronomical units per year. Such a mission would be expensive and technically challenging, but Voyager's success showed it was possible. If a spacecraft built in the 1970s could reach interstellar space, then a modern mission, with better technology and better planning, could do even more. The crossing also affected how astronomers thought about other star systems. If the Sun has a heliosphere with a heliopause, then presumably other stars do too. By studying our own heliosphere, we can learn about stellar winds and their interactions with the interstellar medium in general. Some stars have much stronger winds than the Sun, others have weaker winds. The size and shape of their heliospheres would vary accordingly. By understanding our own system, we gain insight into the diversity of stellar environments across the galaxy. There was also a cultural consequence. Voyager's crossing captured the public imagination in a way that dry astronomical discoveries often don't. It was tangible. A spacecraft, built by humans, had gone farther than anything before. It carried a message from Earth, and now that message was beyond the Sun's direct reach. The golden records, attached to both Voyagers, suddenly felt more significant. They weren't just symbolic gestures. They were actual messages, drifting through actual interstellar space. The chances of anyone finding them are vanishingly small, but the fact that they're out there, beyond the heliopause, makes them real in a way they weren't before. For some people, the crossing sparked existential reflection. If Voyager could leave the Sun's bubble, then perhaps humanity could too. Someday, not just with machines, but in person. The heliopause no longer felt like an unreachable barrier. It felt like a horizon, distant but crossable. For others, the crossing highlighted how vast and empty space is. Voyager 1 travelled for 35 years at tremendous speed, and it only barely left the immediate neighbourhood of the Sun. The nearest star is still tens of thousands of years away at Voyager's speed. The distances are almost incomprehensible. Within the scientific community, the crossing sparked renewed interest in the outer solar system. Funding for surveys and studies increased. New instruments were proposed. Conferences focused on the heliopause, the Kuiper Belt, and the possibility of Planet 9. The discovery of more scattered disk objects accelerated. With better telescopes and more dedicated survey time, astronomers found dozens of new objects beyond Neptune. Each one added to the picture of the outer solar system's structure. The debate about Planet 9 intensified. Voyager's crossing, while not directly related, had shown that the outer solar system was full of surprises. If the heliopause was more complex than expected, maybe there were other surprises waiting. Maybe Planet 9 was real. Educational institutions revised their curricula. Textbooks were updated to include the heliopause as a significant boundary. Planetarium shows featured Voyager's journey. Students learned that the solar system doesn't end at the planets, that there are layers extending far beyond. The immediate ripple, then, was multifaceted, scientific, practical, cultural, educational. Voyager's crossing didn't just answer a question, it opened new questions, inspired new missions, and changed how we teach and think about the solar system. But perhaps the most profound consequence was psychological. Before Voyager, interstellar space was an abstraction. After Voyager, it was a place, a real place, measured and studied, no longer beyond reach. That shift in perception is hard to quantify, but it's real. The universe feels a little smaller, a little more accessible. Not in a literal sense, the distances are still vast, but in a psychological sense, we've touched the edge, we've crossed a threshold, and that makes the next threshold, whatever it is, feel a little less impossible. The immediate ripple created by Voyager's crossing continues to spread. Every year, scientists publish new papers analyzing the data. Every year, mission planners propose new spacecraft to explore farther. Every year, the story of Voyager's journey inspires a new generation to look up and wonder. And every year, Voyager 1 and 2 drift a little farther from home, their signals growing fainter, their power declining. But their legacy, secure. They crossed the heliopause. They showed us the way, and the ripple they created will extend far into the future, shaping how we explore, how we understand, and how we imagine the boundaries of our cosmic home. The consequence, the immediate ripple, reaches into the present moment as you listen to these words. Because Voyager's crossing changed not just science but story. It gave us a narrative arc where before there was only theory. It gave us protagonists, twin spacecraft carrying our messages, journeying into the unknown. And it gave us a chapter ending that promises more chapters to come. The ripple hasn't stopped. It won't stop. Every time someone looks at an image from Voyager, every time a child learns about the heliopause, every time a scientist proposes a new mission to follow in Voyager's path, the ripple spreads farther. That is the nature of genuine discovery. It doesn't just change what we know, it changes what we think is possible. And possibility, once expanded, can never quite contract again. Some discoveries fade with time. They're important for a moment, then superseded by newer findings, relegated to footnotes in textbooks. But others leave echoes that reverberate for generations. Voyager's crossing of the heliopause is one of those. Its impact extends far beyond the immediate scientific findings, into how we understand our place in the universe. The first echo is conceptual. Voyager changed how we define the solar system. Before the crossing, the fucking definition was vague, based mostly on the planets. After, it became clear that the solar system has multiple boundaries, each meaningful in different ways. This multi-layered understanding has spread through education, through popular science, through how people think and talk about space. Ask someone today where the solar system ends, and you might get a nuanced answer. Neptune, or the Kuiper Belt, or the heliopause, or the Oort Cloud. 20 years ago, most would have simply said Pluto or Neptune. The shift in thinking is Voyager's legacy. The second echo is technical. The instruments on Voyager, though primitive by modern standards, proved that long-duration missions to the outer solar system are feasible. Spacecraft can survive for decades in harsh conditions. Power systems can function far beyond their design lifetimes. Communication can be maintained across billions of miles. This technical validation has influenced every subsequent deep space mission. New Horizons, which flew past Pluto in 2015 and then continued into the Kuiper Belt, was designed with Voyager's lessons in mind. Future missions to the outer solar system, whether to the moons of the ice giants or to the heliopause itself, build on the foundation Voyager established. The third echo is inspirational. Voyager's story is a story of persistence. 35 years from launch to the heliopause, 47 years and counting since launch. The spacecraft are still functioning, still transmitting, still traveling. That longevity inspires confidence that humanity can undertake projects spanning generations. Interstellar missions, missions to other stars, will take centuries or millennia with current technology. They require commitment across generations, vision that extends beyond any single human lifetime. Voyager shows that such commitment is possible. It's a proof of concept, not for the journey to the stars, but for the willingness to begin a journey that we won't live to see. Completed. The fourth echo is cultural. The golden records, with their sounds and images of Earth, their greetings in dozens of languages, have become iconic. They represent humanity's desire to connect, to reach out, to say we are here, into the void. The records were curated by a team led by Carl Sagan in the 1970s. They include music from Bach, Beethoven, Chuck Berry, and traditional songs from around the world. They include greetings in languages from ancient Akkadian to modern Mandarin. They include sounds of laughter, of footsteps, of wind and rain. They include images of people, animals, cities, landscapes. In one sense, the records are absurd. The chances of them being found by another civilization are effectively zero. Space is too vast, the Voyagers too small, their trajectories too random relative to other stars. But in another sense, the records are profound. They're a declaration that we exist, that we matter, that our music and languages and laughter deserve to be preserved, even if only as a gesture into eternity. The fact that they're now in interstellar space, beyond the sun's bubble, makes that gesture feel more real. The fifth echo is philosophical. Voyager's crossing forces us to confront the question of boundaries. Where does one thing end and another begin? Is there ever a sharp line? Or is everything in nature a gradient? The solar system, as Voyager showed, is a gradient. Light fades, wind slows, gravity weakens. There's no single point where you can say, this is the edge. Only a series of transitions, each one meaningful, but none definitive. This realization extends beyond astronomy. In biology, where does one species end and another begin when evolution is a continuous process? In geology, where does one tectonic plate end when the boundaries are zones of activity rather than lines? In human affairs, where do cultures, languages, nations truly end when they blend and overlap at their edges? Voyager's legacy is partly this. Boundaries are human constructs, useful but not absolute. Nature favors transitions, not edges. The sixth echo is practical, shaping current research and missions. The heliophysics community, scientists who study the sun and its influence, use Voyager's data as a baseline. Every model of the heliosphere is calibrated against Voyager's measurements. Every prediction of solar wind behavior is tested against what Voyager observed. Meanwhile, the planetary science community uses Voyager's images and data about the outer planets as references. Decades after the flybys, researchers still publish papers analyzing Voyager data, finding new details in the images, new patterns in the measurements, and the astrophysics community, studying the interstellar medium, uses Voyager to understand the local galactic environment. What is the density of particles between stars? What is the strength and direction of magnetic fields? Voyager provides the only direct measurements of these quantities in our neighborhood. The seventh echo is aspirational. Voyager has inspired proposals for follow-on missions. The interstellar probe concept aims to reach 1,000 astronomical units, 10 times farther than Voyager has gone in just 30 years. It would use advanced propulsion and lightweight instruments to study the heliosphere's structure and the interstellar medium beyond. Other proposals envision missions to the outer planet's moons, to Europa, to study its subsurface ocean, to Enceladus, to sample the plumes of water erupting from its south pole, to Titan, to explore its methane lakes and organic chemistry. Each of these missions builds on knowledge gained from Voyager's flybys. The eighth echo is temporal. Voyager will continue to function for another decade, perhaps longer. When it finally falls silent, it will become a time capsule, drifting through space for billions of years. Long after Earth has changed beyond recognition, long after the sun has swelled into a red giant, and then shrunk to a white dwarf, Voyager will still be travelling, still carrying the golden records, still bearing humanity's message. In 40,000 years, Voyager 1 will pass within 1.6 light-years of the star. Gliese 445. It won't be close enough to be captured by that star's gravity. It will simply drift past, one relic from a distant solar system crossing paths with another star's domain. And it will keep going. In millions of years, it may pass near other stars, witness supernovas from a distance, traverse molecular clouds. The spacecraft itself will last effectively forever, barring a collision. The electronics will long since have died. The plutonium will have decayed to inert elements. But the structure, the golden records, the message will endure. This temporal echo, stretching into the deep future, is perhaps the most profound. Voyager is no longer just a mission. It's a monument, a marker of the moment when humanity first reached beyond the sun's immediate embrace and touched the galaxy. The impact, the echoes through time, reach forward and backward, forward into the future, shaping missions and minds for generations to come, backward into the past, connecting us to the vision of the scientists and engineers who built Voyager, who dared to dream of reaching the heliopause when it was only a theoretical concept. And in the present, the echoes resonate in every conversation about the solar system's size, every textbook updated to include the heliopause, every child who learns that we've sent messages into interstellar space. Voyager's impact is not a single thing. It's a cascade of effects, each one building on the others, spreading through science and culture and imagination. It showed us that the solar system is larger than we thought, more complex than we assumed, and more accessible than we dared hope. And it reminded us that exploration is not just about answering questions, it's about asking new ones, about pushing boundaries, about reaching toward horizons we can barely imagine. The echoes of that reminder will continue to reverberate for as long as humanity looks up at the stars and wonders what lies beyond. Behind every spacecraft, behind every discovery, behind every boundary crossed, there are people. Dreamers who looked up and wondered, engineers who turned dreams into metal and circuits, scientists who spent careers studying faint points of light. The solar system's true extent was revealed not by nature volunteering its secrets, but by humans pursuing them. This chapter is about those people, the ones who measured, who calculated, who built, who waited. Let's start with the Voyager team. In the early 1970s, when the mission was being planned, reaching the outer planets felt ambitious enough. Reaching interstellar space was barely discussed. The spacecraft were designed for a 5-year mission to Jupiter and Saturn. Anything beyond that was considered a bonus. The engineers who built Voyager faced enormous challenges. The spacecraft would travel farther from Earth than any before them. They'd experience extreme cold, radiation, and the vacuum of space. They needed to be robust, reliable, autonomous enough to function when communication delays stretched to hours. The team chose to use radioisotope thermoelectric generators for power. Small nuclear batteries, essentially, converting heat from plutonium decay into electricity. It was controversial. Some worried about the safety of launching plutonium into space, but solar panels wouldn't work so far from the sun. Nuclear power was the only option. The instruments had to be miniaturized, hardened against radiation, capable of operating for years without maintenance. Each one was tested exhaustively. Components were selected not for cutting-edge performance, but for reliability. The mission couldn't afford failures. The team that launched Voyager in 1977 was young. Many were in their 20s or 30s. They expected to work on the mission for a few years, see the Jupiter and Saturn encounters, then move on to other projects. But Voyager didn't end. The spacecraft kept functioning, the mission kept extending, and many of those young engineers stayed with it, dedicating decades of their careers to keeping the Voyagers alive. Ed Stone, the project scientist, joined Voyager in 1972. He's still involved today, more than 50 years later. He was there for the launch, for every planetary encounter, for the heliopause crossing. His career has been defined by Voyager, and Voyager has been defined by his steady, patient leadership. Stone often speaks about the privilege of working on a mission that spans generations. Most scientists work on projects that last a few years. Voyager has lasted longer than most careers. It's connected multiple generations of researchers, each one building on the work of the one before. Then there are the astronomers who discovered the Kuiper Belt and scattered disk. David Jewitt and Jane Liu, who spent years searching for objects beyond Neptune, often with little support or recognition. They believed the objects were there, based on theory, but they had to find them to prove it. Night after night, they photographed the same patches of sky. Most nights yielded nothing. The search was tedious, frustrating, and expensive. Telescope time is precious, and spending it on a speculative search was a gamble. But in 1992, their persistence paid off. They found the first object, 1992 QB1, and opened the door to a new population. Within years, hundreds more were discovered. The Kuiper Belt went from theory to confirmed reality. Jewitt later reflected on those years of searching. He described the emotional toll of repeated failures, the pressure to justify the telescope time, the thrill when the first object finally appeared. He said that scientific discovery often requires not just intelligence or skill, but stubbornness, the willingness to keep going when everyone else thinks you're wasting your time. Mike Brown, another key figure, dedicated his career to finding large objects in the outer solar system. He discovered Eris, Haumea, Makemake, and several others. Each discovery refined our understanding of the Kuiper Belt's population and structure. Brown's discoveries also led to Pluto's reclassification. He didn't set out to kill Pluto, as he jokingly put it later. He set out to find what was out there. But the fact that Eris was as large as Pluto forced the question of what constitutes a planet. The International Astronomical Union's decision to reclassify Pluto was a consequence of Brown's work, whether he intended it or not. Brown has spoken about the strange mix of emotions that came with that. Pride in the discoveries, but also guilt about Pluto. He knew many people felt a connection to Pluto, and he knew his work had contributed to its demotion, but he also believed the decision was scientifically correct. Pluto belongs to a family, and recognizing that family is more important than preserving Pluto's status as a planet. Then there's Konstantin Batygin and Mike Brown again, this time proposing Planet 9. They spent years analyzing the orbits of distant objects, running simulations, refining models. The work is painstaking. Each new object discovered requires recalculating, checking whether it fits the pattern or breaks it. Planet 9 remains hypothetical, but the search for it has energized the field. Other astronomers have joined the hunt, using different telescopes and different strategies. Some believe the planet is real, others remain skeptical. But everyone agrees the question is worth pursuing. Beyond the famous names, there are hundreds of others who've contributed. Telescope operators who spend cold nights at observatories, guiding instruments to precise positions. Data analysts who process terabytes of images, searching for faint moving points. Software engineers who write the algorithms that detect objects automatically. Theorists who model orbits and gravitational interactions. Educators who translate the discoveries into lessons for students. Each person plays a part in the collective effort to understand the solar system's extent. Science is not a solitary pursuit. It's collaborative, cumulative, built on the work of countless individuals over decades or centuries. There's also a generational element. The people who launched Voyager are retiring or have already passed away. The people who discovered the first Kuiper Belt objects are now senior scientists, training the next generation. The students who learn about the heliopause today will be the ones proposing missions to study it in the future. This passing of knowledge from one generation to the next is how science progresses. No single person can see the full picture, but each person adds their piece, and over time, the picture emerges. There's a human element to the waiting, too. Voyager took 35 years to reach the heliopause. Searches for distant objects take decades. Theories about Planet 9 may not be confirmed or disproven for years. Patience is required. The willingness to start something knowing you may not see it finished. This is different from most human endeavors. In business, in politics, in daily life, we expect quick results. We want to see the impact of our work within months or years. But in astronomy, especially in studying the outer solar system, the timescales are longer. You plant seeds knowing someone else will harvest them, and yet people do it. They dedicate careers to it. They pour energy and passion into questions that may not be answered in their lifetimes. Why? For some, it's curiosity, the need to know, to understand, to solve the puzzle. For others, it's the beauty of the work itself, the elegance of an orbit calculated precisely, the thrill of discovering something to one has seen before, the satisfaction of building something that works. For others still, it's connection to the cosmos, to history, to humanity's long journey of exploration. to be part of the effort to push boundaries, to extend our reach, to answer the ancient question of what's out there. The human element is what makes the story of the solar system's extent more than a collection of facts. It's a story of people reaching beyond themselves, beyond their lifetimes, towards something larger. Ed Stone, now in his 80s, still talks about Voyager with the same enthusiasm he had in 1972. His voice carries decades of knowledge, but also wonder. After 50 years, the mission still surprises him. David Dewitt still searches for distant objects, still publishes papers, still mentors students. The Kuiper Belt he helped discover is now a major field of study, with dozens of researchers around the world. The engineers who maintain communication with Voyager work with equipment that's older than some of them are. They've learned systems built before they were born, keeping them running through ingenuity and dedication. And somewhere, a student is looking at data from a telescope, searching for a faint moving point that might be a new object in the scattered disk. Or a theorist is running a simulation, testing whether a particular orbit could be shaped by an unseen planet. Or an engineer is designing an instrument for a future mission to the heliopause. The human element is continuous. It doesn't stop. As long as there are people who look up and wonder, the effort to understand the solar system's extent will continue. The dreamers are not just the famous scientists whose names appear in textbooks. They're everyone who contributes, in small ways or large, to the collective project of exploration. The telescope technicians, the data archivists, the educators, the communicators, the funders who support the research, the public who cares enough to pay attention. All of them are part of the story. All of them help push the boundary of what we know a little farther outward. And in a sense, all of us who wonder about these questions are part of it too. Every time we look up at the night sky and think about how far things go, every time we marvel at images from distant worlds, every time we feel connected to something larger than ourselves, we're participating in the human element of exploration. The solar system's extent is measured in astronomical units and light years, but it's discovered and understood through human curiosity, persistence, and collaboration. The measurements are precise. The human element is messy, emotional, flawed, but it's the human element that makes the measurements possible. Without the dreamers, the solar system would still be vast. But we wouldn't know how vast. We wouldn't have seen the images. We wouldn't have crossed the boundaries. We wouldn't have sent our messages into the dark. The dreamers are the reason we know as much as we do. And the dreamers of tomorrow will be the reason we learn even more. The human element, passed from generation to generation, is what transforms distant points of light into worlds, and abstract distances into journeys worth taking. Science is often portrayed as a smooth progression of knowledge. One discovery leads to another, each building on what came before, but the reality is messier. Science advances through argument, through skepticism, through people disagreeing about what the data means. The question of where the solar system ends has been no exception. Every claim, every boundary proposed, every theory put forward has faced opposition, and often that opposition has been necessary and valuable. When Gerard Kuiper proposed in 1951 that a belt of debris might exist beyond Neptune, many astronomers were skeptical. The idea made theoretical sense. The protoplanetary disk from which the planets formed shouldn't simply end at Neptune. There should be leftovers. But theoretical sense isn't proof. And in the 1950s, telescopes weren't powerful enough to detect such objects. So the Kuiper Belt remained a hypothesis, interesting but unproven. For decades, the opposition wasn't hostile. It was simply cautious. Without evidence, the belt couldn't be accepted as fact. And that caution was reasonable. Science shouldn't accept ideas on theoretical grounds alone. When the first Kuiper Belt object was finally discovered in 1992, the opposition didn't vanish immediately. One object could be an outlier. Perhaps it was a captured comet or a rogue body from elsewhere. More evidence was needed. As more objects were found, the skepticism faded. By the late 1990s, the Kuiper Belt's existence was undeniable, but opposition shifted to other questions. How large was the belt? How many objects did it contain? How did it form? Each question sparked debate. Different models made different predictions. Data was often ambiguous, fitting multiple explanations. Scientists argued not because they wanted to be difficult, but because argument is how truth gets refined. The reclassification of Pluto in 2006 was one of the most contentious battles in recent astronomy. The opposition was fierce, and it came from multiple directions. Some astronomers argued that Pluto should remain a planet regardless of what else was discovered. It had been a planet for 76 years. Generations had learned it as the ninth planet. Changing that definition felt arbitrary and disruptive. Others argued that clearing the orbit, the criterion Pluto failed, was too restrictive. Even Earth shares its orbit with near-Earth asteroids. Jupiter has Trojan asteroids co-orbiting with it. Why should these worlds be considered planets while Pluto wasn't? The debate became heated. At the International Astronomical Union meeting in Prague, astronomers proposed multiple definitions, argued over wording, and ultimately voted. The decision to create the dwarf planet category and reclassify Pluto passed, but not unanimously. Many disagreed. The public opposition was even stronger. Online petitions gathered thousands of signatures calling for Pluto to be reinstated. Schools in New Mexico, where Clyde Tombaugh had discovered Pluto, passed resolutions declaring that Pluto would always be a planet in their state. Alan Stern, the principal investigator of the New Horizons mission to Pluto, vocally opposed the reclassification. He argued that the definition of clearing the orbit was meaningless. What mattered, he said, was whether an object was large enough to be spherical and geologically active. By that measure, Pluto qualified as a planet. The battle over Pluto's status continues to this day, though with less intensity. Most astronomers have accepted the dwarf planet category as useful, but some still argue for a different definition that would include Pluto as a planet. This opposition has been valuable. It's forced astronomers to think carefully about what they mean by planet, to articulate why certain definitions are useful and others aren't. The debate hasn't produced universal agreement, but it's produced clarity. The Planet 9 hypothesis has faced similar opposition. When Konstantin Batygin and Mike Brown published their paper in 2016, reaction was mixed. Some astronomers found the evidence compelling. The clustering of orbits seemed too strong to be coincidental. Others were skeptical. The sample size was small, fewer than a dozen objects. Observational bias could easily produce apparent clustering where none existed. Surveys don't cover the sky evenly. Some regions are observed more thoroughly than others, which could create an illusion of alignment. Critics also pointed out that finding a planet at several hundred astronomical units is extraordinarily difficult. It would be incredibly faint, perhaps magnitude 22 or fainter. Even large, telescopes would struggle to detect it. If Planet 9 existed, why hadn't it been found already? Proponents countered that the outer solar system is vast and poorly surveyed. A faint, slow-moving object could easily be missed. And the clustering of orbits provided indirect evidence that something massive was out there. The debate has been productive. It spurred searches for Planet 9 using different telescopes and strategies. It's led to better surveys of the outer solar system. It's refined models of how planetary migration and gravitational interactions shape orbits. Whether Planet 9 exists or not, the opposition has ensured that the hypothesis is tested rigorously. That's how science should work. Extraordinary claims require extraordinary evidence, and the burden is on proponents to provide it. The heliopause itself faced opposition in its early days. Before Voyager, some scientists questioned whether a clear boundary even existed. They argued that the transition from solar to interstellar space might be gradual, with no distinct edge. Voyager's crossing settled that debate, mostly. The heliopause is real, measurable, a distinct change in particle environment. But even now, details are disputed. The structure of the boundary layer, the behavior of magnetic fields, the dynamics of the transition, all these are active areas of research with competing theories. Opposition also arises when findings contradict established models. When Voyager 1 crossed the heliopause and the magnetic field didn't flip direction as predicted, some scientists initially doubted the crossing had occurred. If the field hadn't changed, how could Voyager truly be in interstellar space? It took careful analysis of all the data, not just magnetic fields, but particle counts and plasma measurements, to confirm the crossing. The models were wrong about the magnetic field behavior, but right about the overall structure. The opposition forced a deeper examination, which ultimately strengthened the conclusion. There's also opposition between different communities. Planetary scientists, heliophysicists, and astrophysicists sometimes have different priorities and perspectives. What one group considers the most important boundary, another might view as less significant. Planetary scientists often focus on solid bodies, planets, and dwarf planets and moons. For them, the outer edge of the Kuiper Belt, or scattered disk, might feel like the natural boundary of the solar system. Heliophysicists study the sun and its influence. For them, the heliopause is the key boundary, the place where solar plasma gives way to interstellar plasma. Astrophysicists studying the interstellar medium might focus on the Oort Cloud or the Hill sphere, the regions where the sun's gravity interacts with galactic tides. Each group has valid reasons for their focus, but their different perspectives can lead to disagreement about which boundary matters most. This isn't a flaw, it's a feature. Different perspectives illuminate different aspects of the truth. The battle for truth, then, is not a single conflict, but an ongoing process. Every claim is tested, every theory is questioned, every boundary is debated, and through that process, understanding deepens. Opposition in science is not obstruction, it's quality control. It ensures that ideas are tested rigorously, that evidence is examined carefully, that conclusions are justified. Without opposition, without skepticism, science would accept ideas too easily and errors would accumulate. The astronomers who opposed the Kuiper Belt's existence in the 1960s weren't wrong to be skeptical. They were doing their job, requiring proof before acceptance. When proof came, they accepted it. The scientists who debate Planet 9 today aren't being obstructionist. They're ensuring that the hypothesis is tested thoroughly. If Planet 9 exists, it will be found, and the debate will be settled. If it doesn't, the debate will have pushed the field forward anyway, through better surveys and deeper understanding of orbital dynamics. Even the opposition to Pluto's reclassification, emotional as it was, served a purpose. It forced astronomers to articulate clearly why definitions matter, why the dwarf planet category is useful, why the number of planets shouldn't be arbitrary. The battle for truth is ongoing. New data brings new questions. New theories bring new opposition. And that's healthy. That's how science works at its best. For those of us outside the scientific community, the battles can seem confusing. Why can't scientists agree? Why do they keep changing their minds? Isn't science supposed to provide clear answers? But the battles are not a sign of weakness. They're a sign of rigor. Science doesn't claim to have all the answers. It claims to have a process for getting closer to the truth, step by step, through testing and debate. The solar system's extent is still being battled over, in a sense, not with hostility, but with careful argument. Where does it end? At Neptune? Or the heliopause? Or the Oort Cloud? Each answer has defenders, each has critics, and the debate continues. And that's appropriate, because the question is complex, and simple answers don't do it justice. The battle for truth, in this case, is the recognition that truth itself is layered, that boundaries are not absolute, that multiple perspectives can all be valid. The opposition, the skepticism, the debate, all of it serves to refine our understanding, to test our assumptions, to ensure that what we believe is justified by evidence, not just by hope or tradition or convenience. And so the battle continues, not to tear down, but to build up, not to create confusion, but to create clarity. The opposition is not the enemy of truth, it's the guardian of it. There comes a moment, sometimes sudden, sometimes gradual, when the pieces fall into place, when scattered facts coalesce into understanding, when you see not just the parts, but the whole. For astronomers studying the solar system's extent, that awakening has been unfolding over decades. But for many, there was a particular moment when it crystallized, when they realized that the solar system is not what they thought it was. For some, it was seeing the first images from Voyager. The outer planets, revealed in stunning detail, were nothing like the smooth, featureless spheres imagined before. They were worlds, dynamic and complex, with storms and moons and rings. If the outer planets were that interesting, what else might be waiting in the farther reaches? For others, the awakening came with the discovery of the Kuiper Belt. The realization that beyond Neptune lay not emptiness, but a vast population of objects. The solar system suddenly expanded, not by a little, but by a factor of 10 or more. For still others, it was Voyager's crossing of the heliopause, the moment when a spacecraft actually left the sun's bubble and entered interstellar space. It made the boundary real, tangible, not just a theoretical concept. But beyond individual moments, there's been a broader awakening, a shift in how we understand our place in the universe. And that awakening has implications far beyond astronomy. The first aspect of this awakening is scale. We've realized that the solar system is vastly larger than the bright inner planets suggest. The region we think of as the solar system, the planets and asteroid belt, occupies only a tiny fraction of the sun's domain. If you drew the solar system to scale, with Earth the size of a grain of sand, Neptune would be about a foot away. The heliopause would be about 3 feet. The inner edge of the Oort Cloud would be half a mile, and the outer edge might be 6 miles away. Most of the solar system is empty space, scattered debris, and faint sunlight. The planets, for all their importance to us, are almost incidental. This realization is humbling. It shows how small we are, how concentrated in a tiny region, but it's also awe-inspiring. To realize that the sun's influence reaches so far that we're part of a structure measured in light years is to feel connected to something immense. The second aspect is layering. We've awakened to the fact that the solar system doesn't have a single edge, but multiple edges. Each one marks a different transition. Each one is meaningful. This layered understanding changes how we think about boundaries in general. In nature, transitions are rarely sharp. They're gradual, overlapping, complex. The solar system's structure reflects that truth. And if boundaries in space are layered, what about boundaries elsewhere? National borders are drawn as sharp lines, but cultures blend. Language boundaries are fuzzy, with dialects transitioning gradually. Even personal boundaries, the sense of where I end and you begin, are less clear than we like to think. The solar system's layered boundaries are a lesson in accepting complexity, in recognizing that reality doesn't fit neatly into categories. The third aspect is connection. We've awakened to the fact that the solar system is not isolated. It's part of the galaxy, influenced by neighboring stars, shaped by galactic tides, connected to the interstellar medium. The Sun doesn't exist in a vacuum. It orbits the galactic center, passing through different regions, encountering molecular clouds and stellar clusters. The Oort Cloud is stirred by passing stars. The heliopause flexes in response to interstellar conditions. Even the planets may have been influenced by stellar encounters in the Sun's youth. This connection is profound. It means the solar system has a history that extends beyond its own formation. It's been shaped by the galaxy, and in turn, it shapes its immediate environment. We're not separate from the universe. We're embedded in it. The fourth aspect is time. We've awakened to the vast timescales involved in the outer solar system. Orbits that take millions of years. Comets that visit once in human history and won't return for countless generations. Structures that formed billions of years ago and have barely changed since. This awareness of deep time is both disorienting and grounding. Disorienting because it makes human timescales seem infinitesimal. The rise and fall of civilizations happens in the blink of an eye, compared to the orbit of an Oort Cloud object. But it's also grounding. It reminds us that we're part of something older and larger than ourselves. The atoms in our bodies were forged in stars billions of years ago. The water we drink may have been delivered by comets from the outer solar system. We're not separate from this ancient dance. We're participants in it. The fifth aspect is perspective. We've awakened to the fact that our view from Earth is limited, biased, incomplete. We see the solar system from one angle. At one moment in cosmic time, other perspectives would reveal different truths. From Neptune, the Sun would be just a bright star. From the Oort Cloud, it would be barely distinguishable from other stars. From outside the solar system, looking in, the structure would appear different still, perhaps as a faint glow of the heliosphere, or as a tiny gravitational influence on passing objects. This multiplicity of perspectives is important. It reminds us that what we see depends on where we stand, and that to understand fully, we need to imagine other vantage points, other ways of seeing. The sixth aspect is mystery. We've awakened not to complete understanding, but to deeper questions. The discovery of the Kuiper Belt led to questions about its formation. The crossing of the heliopause revealed complexities we didn't predict. The possibility of Planet 9 opens entire new avenues of inquiry. Every answer generates new questions, and that's not a failure. It's how knowledge grows. The awakening is not to final truth, but to the process of discovering it. For the public, the awakening has been slower and more diffuse. Most people still think of the solar system as the planets, but awareness is growing. Popular science articles mention the heliopause. Documentaries feature the Kuiper Belt. Students learn that the solar system is larger than the textbooks used to say. This gradual awakening matters, because how we understand the solar system shapes how we understand our place in the universe. If we think of the solar system as small and well-defined, we might feel separate from the larger cosmos. But if we understand it as vast, layered, and connected to the galaxy, we feel more integrated into something larger. The awakening is also practical. It shapes mission planning. If we understand the solar system's full extent, we can plan missions to explore it. We can prioritize certain boundaries over others. We can design instruments to study transitions we now know exist. It shapes education. Textbooks are being rewritten to include the Kuiper Belt, the heliopause, the Oort Cloud. Students learn about the solar system's layered structure. Future generations will grow up with a more accurate, more complex understanding than previous ones, and it shapes imagination. When we know the solar system is vast, we dream bigger. We imagine missions not just to Mars, but to the outer solar system and beyond. We think about humanity's future as interstellar, not just interplanetary. The awakening, then, is not a single moment but a process. It's ongoing. Every new discovery adds to it. Every refined model deepens it. Every mission extends it. And for each of us individually, the awakening can happen at any time. Perhaps it's happening now, as you listen to this. Perhaps you're realizing for the first time just how large the solar system truly is, how layered, how connected to the galaxy, how much remains to be explored. That realization, that awakening, is a gift. It expands your sense of scale, your sense of time, your sense of possibility. It connects you to something ancient and vast, and it invites you to be curious, to ask questions, to wonder what else might be waiting in the darkness, just beyond the edge of what we know. The awakening is not complete. It never will be. There will always be more to learn, more to discover, more to understand. But each step of awakening brings us closer to seeing the solar system and our place in it, as it truly is. Vast, complex, beautiful, and far stranger than we ever imagined. After travelling outward through layers of ice and plasma and gravity, after tracing boundaries that shift and fade, after considering multiple definitions and perspectives, we arrive at something deeper than any single answer. The revelation, the deepest truth about where the solar system ends, is this: it doesn't. Not in the way we typically think of endings. Not with a wall or a line or a moment when you're clearly on one side or the other. The solar system ends the way a conversation fades when two people walk in opposite directions, gradually, imperceptibly, until you're no longer sure when the words stopped and the silence began. This revelation is both simple and profound. Simple because it's obvious once stated. The sun's influence doesn't stop abruptly at any distance. It fades. Light dims with the inverse square of distance. Gravity weakens continuously. The solar wind eventually yields to interstellar pressure, but the transition is a zone, not a line, and profound because it challenges our fundamental desire for clear categories. We want things to be one way or another, inside or outside, here or there, ours or not ours. But the universe doesn't accommodate that desire. Nature favors gradients, transitions, continuums. The solar system is not a box. It's a sphere of influence that fades gradually into the galaxy. This truth applies to every proposed boundary. The heliopause, for all its reality as a measurable transition, is not a sharp edge. It's a region, perhaps several astronomical, units thick, where solar and interstellar plasma mix and compete. Cross it, and you're not suddenly somewhere completely different. You're in a transitional zone, where both influences persist. The Oort Cloud, if it exists, doesn't have a crisp outer edge. It fades. The density of objects decreases gradually with distance until at some point There's no meaningful difference between the outermost Oort Cloud objects and random debris drifting between stars. Even gravity, which technically extends infinitely, has a practical limit. The Hill sphere marks where the sun's pull is overtaken by galactic tides. But that transition is gradual too. There's no moment when the sun's gravity drops to zero. It simply becomes less important than other forces. The revelation, then, is that asking where the solar system ends is asking the wrong question. The right question is, how does the sun's influence fade? And the answer is, gradually, in layers, each layer defined by a different kind of plekler, influence, each fading at a different rate. This truth has implications beyond astronomy. It speaks to how we understand boundaries in general. We draw borders on maps, lines between countries, edges between properties. We create categories and definitions, trying to impose order on reality. But reality is messy. Borders are human constructs, useful for administration and politics, but not reflective of how people, cultures, and ecosystems actually behave. They blend, they overlap, they defy the lines we draw. The solar system's lack of a clear edge is a reminder that nature doesn't respect our categories. We can define the edge in multiple ways, and each definition is valid for certain purposes, but none captures the full truth, because the full truth is that there is no edge, only a fading. This revelation also changes how we think about exploration. If the solar system doesn't end sharply, then leaving it is not a discrete event. Voyager 1 crossed the heliopause, but it's still in the solar system by other measures. It left in one sense and will never leave in another. Future missions will face the same ambiguity. A spacecraft could pass through the outer Oort Cloud, trillions of miles from the sun, and still be within the sun's gravitational influence. It would be in interstellar space by every practical measure, yet still technically part of the solar system. This matters because it affects how we think about interstellar missions. Reaching another star is not just about crossing the edge of the solar system. It's about crossing vast expanses of interstellar space, beyond any reasonable definition of the sun's domain. The nearest star, Proxima Centauri, is 4.2 light-years away. Even if the Oort Cloud extends 2 light-years, that leaves more than 2 light-years of truly interstellar space to cross. The journey to another star is not just a long journey through the solar system, it's a journey beyond, into the gulf between stars. The revelation also has philosophical weight. If the solar system doesn't end, what does that say about other boundaries we take for granted? Where does the atmosphere end and space begin? There's no sharp line. The Kármán line at 100 kilometers altitude is a convention, not a physical boundary. Air doesn't stop there. It just becomes very, very thin. Where does the ocean end and the land begin? The tide line shifts. Wetlands blur the boundary. Rivers connect ocean to continent. The edge is a transition zone, not a line. Where does one ecosystem end and another begin? Forests don't stop sharply at the edge. They thin gradually into grasslands or deserts. Species ranges overlap. The boundaries we draw on ecological maps are approximations of something more complex. The revelation about the solar system's edge invites us to see all boundaries with new eyes, to recognize that they're often gradual, fuzzy, context-dependent, to accept that ambiguity is not a failure of knowledge, but a reflection of reality. In a sense, this is a lesson in humility. We want to know where things end. We want clear answers. We want the universe to be knowable, categorizable, neat, and in many ways it is. We can measure distances, calculate orbits, predict phenomena with extraordinary precision. But precision doesn't always give us the clarity we seek. We can measure the heliopause to within a few astronomical units. We can calculate the Hill sphere to high accuracy. But those measurements don't tell us the edge of the solar system. They tell us about different kinds of edges, each one partial, each one true in its own way. The revelation is that truth itself is layered. Multiple answers can coexist, each valid from different perspectives. The solar system ends at Neptune if you define it by major planets. It ends at the heliopause if you define it by solar wind. It ends at the Oort Cloud if you define it by gravitationally bound objects. And it never ends if you define it by the sun's influence, which fades asymptotically but never reaches zero. All of these are true, none is complete. Together, they paint a picture of a structure far more complex than any single definition could capture. For scientists, this revelation is liberating. It means they don't have to argue about which boundary is correct. They can acknowledge that different boundaries serve different purposes. A mission planner might care about the heliopause. A comet researcher might care about the Oort Cloud. A gravitational theorist might care about the Hill sphere. Each perspective is valid. For educators, it's challenging. How do you teach something that doesn't have a simple answer? But it's also an opportunity to teach students that complexity is normal, that ambiguity is acceptable, that multiple truths can coexist. These are valuable lessons, applicable far beyond astronomy. For anyone lying awake at night, pondering the edges of things, it's comforting. The solar system doesn't end sharply, because nothing in nature does. Everything fades, blends, transitions, and that's okay. That's how the universe is built. The deepest truth, then, is not a distance or a boundary. It's a recognition that the solar system, like so much in nature, defies singular definition. It's a gradient, a fade, a slow transformation from one state to another, and in that recognition, there's beauty, because it means we're not separate from the galaxy. The solar system doesn't stop at some wall that divides us from everything else. It fades into the galaxy, blends with it, becomes part of it. We're not isolated, we're connected, and the boundary that doesn't exist is proof of that connection. The solar system and the galaxy are not two distinct things with a sharp line between them. They're one continuous structure, and we're part of it. That's the revelation. That's the deepest truth. Not an ending, but a fading. Not a boundary, but a transition. Not separation, but continuity. The solar system doesn't end. It becomes. And in becoming, it connects us to everything beyond. We've travelled outward together, from Earth to Neptune, through the Kuiper Belt and scattered disk, across the heliopause, into the theoretical reaches of the Oort Cloud. We've measured distances, crossed boundaries, considered definitions. But before we return home, there's value in pausing, in reflecting on what it all means. What does it mean that the solar system is so vast, that its edges are so ambiguous, that its influence fades so gradually into the galaxy? For one thing, it means our cosmic address is more complex than we might have thought. We don't just live on Earth. Third planet from the Sun, we live deep inside a layered structure that extends perhaps 2 light years in radius. We're near the centre of an enormous domain, most of which we'll never see directly. This perspective is humbling. The planets, which seem so significant to us, occupy only the innermost shell of the Sun's influence. The Kuiper Belt is 50 times farther out, the heliopause more than 100 times, the Oort Cloud thousands or tens of thousands of times. We're like someone living in the heart of a vast city, convinced that the few blocks they can see are the whole of it. but the city extends for miles in every direction. Most of it is invisible from our vantage point, but it's there, connected to where we stand. The vastness also means we have much left to explore. We've sent spacecraft to the edge of the heliosphere, but not beyond. We've discovered thousands of Kuiper Belt objects, but likely not even 1% of what's there. We've never directly observed an Oort Cloud object. We may not even have found all the major planets. The solar system, for all our study, remains mostly unexplored. And that's exciting. It means there are discoveries waiting, mysteries to solve, wonders to uncover. It means future generations will see things we can't imagine, will answer questions we haven't yet thought to ask. The ambiguity of the boundaries means something too. It means reality is more complex than our definitions. We can measure, calculate, categorize, but nature doesn't conform to our boxes. It spills over, blends, resists our attempts to simplify it. This is a lesson worth carrying beyond astronomy. In human affairs, we often seek clarity that doesn't exist. We want to know where one thing ends and another begins. Good or bad, right or wrong, ours or theirs. But the universe suggests that such sharp divisions are rare. Most things exist on gradients, in shades of grey, in transitional states. Accepting ambiguity doesn't mean abandoning rigour or precision. We can still measure carefully, think clearly, communicate accurately, but it means recognizing that precision doesn't always yield simplicity. Sometimes the most accurate answer is, it depends, or it's both, or it transitions gradually. The gradual fading of the sun's influence also carries meaning. It shows that nothing is truly isolated. The solar system doesn't stop at some wall that separates us from the rest of the universe. It fades into the galaxy, connects to it, becomes part of it. This connection is literal, not metaphorical. The sun orbits the galactic center. It passes through different regions, encounters molecular clouds, feels the pull of nearby stars. The solar system is shaped by these interactions, and in turn, it shapes its environment. The heliosphere is a bubble, but it's a bubble moving through a medium, not floating in nothingness. And if the solar system is connected to the galaxy, then we are too. The atoms in our bodies came from stars that exploded long before the sun formed. The elements we're made of are galactic in origin. The water we drink, the air we breathe, the ground we stand on, all of it has a history that extends beyond the solar system. We're not separate from the cosmos. We're an expression of it, a momentary organization of matter that can think, feel, wonder. The solar system's lack of a clear edge is a reminder that there are no clear edges anywhere. Everything connects to everything else, in ways obvious and subtle. Pondering the meaning of the solar system's extent also brings us to questions of time. The structures we've explored formed over billions of years. The Oort Cloud, if it exists, is as old as the sun. The scattered disk records gravitational interactions from the solar system's youth. The heliopause changes shape over decades, but has existed for billions of years. These timescales dwarf human experience. All of recorded history, all of civilization, is a tiny fraction of the solar system's age. We're newcomers, brief inhabitants of a system that existed long before us and will continue long after. Yet we're here now, in this moment, able to study and understand, able to send spacecraft across billions of miles, able to detect faint objects at the edge of the sun's influence, able to ask where the solar system ends and to grapple with the complexity of the answer. That ability, that capacity for curiosity and exploration is itself meaningful. It means that even though we're small and brief, we're not insignificant. We can reach beyond ourselves, extend our awareness across vast distances and times. We can understand structures far larger than our lives. There's also meaning in the human response to these discoveries. The fact that people care about Pluto's status, that they debate Planet 9, that they feel wonder when Voyager crosses the heliopause, all of this matters. It shows that exploration is not just a scientific endeavor. It's a human one, driven by curiosity, creativity, and a desire to connect with something larger. The solar system's vast extent invites us to dream, to imagine future missions that will travel farther, explore more, answer questions we can't yet formulate, to picture a time when humanity might spread beyond Earth, not just to Mars or the moons of Jupiter, but to the outer reaches, perhaps even to other stars. Those dreams are still distant. The challenges are immense, but the fact that we dream them at all is significant. It shows that exploration is part of who we are as a species. We're not content to stay in one place. We look outward, always, toward the next horizon. And finally, there's meaning in the journey itself. Not just the physical journey of spacecraft, but the conceptual journey we've taken tonight. From familiar planets to icy belts to plasma boundaries to theoretical clouds of comets. From clear definitions to ambiguous transitions to the recognition that endings are really fadings, the journey mirrors the structure it explores. It doesn't conclude sharply. It fades, leaving us with questions as much as answers. Where does the solar system end? It depends on what you measure. How far does the sun's influence reach? As far as you're willing to look. What does it mean to belong to the solar system? Perhaps just that you're part of this vast, connected, gradually fading structure we call the sun's domain. Reflecting on these meanings, we find not closure but opening. Not a final answer, but an invitation to keep wondering. The solar system's extent is not just a fact to be learned. It's a lens through which to see our place in the universe differently. We're part of something vast, something layered, something connected to the galaxy and beyond. And though we occupy only a tiny region of it, though our lifetimes are brief compared to its age, we're here. We're aware. We're reaching outward. And that, perhaps, is the deepest meaning of all. Not where the solar system ends, but that we're here to ask the question. That we can wonder about boundaries and fading and connection. That we can send our emissaries across billions of miles and receive their whispers back. The reflection, then, brings us not to conclusions, but to appreciation for the vastness, for the complexity, for the mystery that remains, and for our place in it all, however small, however brief, however far from the edge. The meaning we find in pondering the solar system's extent is ultimately personal. For some, it sparks scientific curiosity. For others, spiritual wonder. For still others, a simple appreciation for the complexity of nature. All these responses are valid. All are part of the human experience of encountering something vast and beautiful and beyond complete understanding. As we prepare to return from this journey, we carry with us not just facts and figures, but a deeper sense of context, a knowledge that we inhabit not just a planet, but a system. Not just a system, but a gradient that fades into the galaxy. And in that gradient, in that slow transformation from solar to galactic, we find our place, connected, part of the whole, home in a way that encompasses far more than we ever imagined when we first looked up at the night sky and wondered how far it all goes. And so we return, from the cold outer darkness where sunlight is no brighter than starlight, where objects orbit for millions of years, where the galaxy's influence begins to overtake the sun's, we return inward, watching the sun grow brighter, the planets emerge from the void, Earth appear as more than a point of light. We return with new understanding. The solar system is not the tidy collection of 8 planets we learned about as children. It's a vast, layered structure that extends far beyond the bright inner worlds. It has multiple boundaries, each real, each meaningful, none definitive. And it fades gradually into the galaxy, rather than ending sharply. This understanding is the legacy of centuries of observation, decades of exploration, and countless hours of human thought. It's built on the work of astronomers who tracked comets, engineers who built spacecraft, theorists who modeled gravitational interactions, and everyone who looked up and wondered. The legacy includes the spacecraft themselves, Voyager 1 and 2, still travelling outward, still transmitting their faint signals. They've crossed the heliopause and entered interstellar space. In tens of thousands of years, they'll pass near other stars. In millions, they'll still be travelling, silent monuments to human curiosity. New Horizons, which flew past Pluto in 2015, continues into the Kuiper Belt. It may encounter other objects, send back more images, expand our knowledge of that frozen frontier. Eventually, like Voyager, it too will fall silent and continue alone. Future missions will follow. The interstellar probe, if funded, could reach 1,000 astronomical units, 10 times farther than Voyager has gone. Other proposals aim for the outer planet's moons, the Oort Cloud, or even to search for Planet 9. Each mission adds to the legacy. Each one extends our reach, deepens our understanding, pushes the boundaries of what's possible. The solar system's extent is no longer just a theoretical question. It's a practical frontier, something we can explore, measure, and understand. The legacy also lives in education. Today's students learn about the Kuiper Belt and heliopause alongside the planets. They understand that the solar system is more complex than previous generations were taught, and they carry that understanding forward, building on it, expanding it. The discoveries of the past few decades have reshaped textbooks, planetarium shows, and online resources. The solar system presented to children today is vastly different from the one presented 50 years ago. And that's progress, not just in knowledge, but in how we teach, how we think, how we imagine. But the legacy is not just scientific or educational, it's cultural. The images from Voyager, the discoveries of the Kuiper Belt, the crossing of the heliopause, all of these have entered the public consciousness. They're part of our shared story, part of how we understand ourselves as a species. We're the species that sent messages to the stars, that crossed into interstellar space, that discovered worlds beyond Neptune and named them after gods and legends, that asked how far the solar system reaches and pursued the answer across decades and billions of miles. That story, that legacy, shapes how we see our place in the universe. It tells us we're explorers, curious and creative, capable of reaching beyond our immediate surroundings. It tells us we're part of something larger, connected to the cosmos in ways both literal and profound. And now, as we return from this journey outward, we bring that story home. We bring the knowledge that the solar system is vast, that its boundaries are layered and ambiguous, that it connects to the galaxy in ways we're only beginning to understand. But we also bring something simpler, a renewed appreciation for Earth, for the pale blue dot suspended in a sunbeam, as Carl Sagan described it, for the only world we know that harbours life, that cradles consciousness, that gives rise to minds capable of wondering about the edges of things. From the perspective of the outer solar system, Earth is insignificant, a tiny rock orbiting an ordinary star, but it's also everything. It's home. It's where every human who ever lived was born, grew up, dreamed, loved, and died. It's where the story began and where, for now, it continues. The journey outward teaches us about the solar system, but the return teaches us about home, about how rare and precious it is, about how much depends on this one small world in the vast dark. That lesson is part of the legacy too. Exploration isn't just about discovering what's out there. It's about understanding what's here, about seeing our home with new eyes, informed by context and scale. As we settle back into familiar territory, the planets take on new meaning. Mars is no longer just the fourth planet, but a stepping stone toward the outer system. Jupiter is no longer just a large world, but a gravitational shepherd that shaped the Kuiper Belt and scattered disk. Neptune is no longer the edge, but a gateway to the frontier beyond. And the sun, which gives us light and warmth and life, is revealed as a star like billions of others, carrying with it a retinue of worlds and debris and fields, all bound by gravity and shaped by time. The closing of this journey is not an ending. It's a transition, like all the boundaries we've explored. We've reached the farthest points we can currently measure and begun the return. But the exploration continues. New missions will venture farther. New discoveries will refine our understanding. New questions will emerge. The solar system's story is ongoing. It was here long before us. 4.6 billion years of planetary formation and orbital evolution and cometary bombardment. And it will continue long after us, as the sun slowly brightens, as planets shift in their orbits, as the Oort Cloud continues its slow dance with the galaxy. We're witnesses to a moment in that story. Brief observers of a structure that extends across space and time in ways we can barely comprehend. But we're also participants. Our spacecraft travel outward. Our instruments measure and record. Our minds interpret and understand. We're not passive. We engage with the cosmos, actively seeking to know it. That engagement is the legacy. Not just what we've learned, but that we've learned it. That we've cared enough to look, to measure, to wonder. That we've built machines to extend our senses across billions of miles. That we've asked difficult questions and grappled with complex answers. And so we return, not to where we started, but to where we've always been, on Earth, near the sun, deep inside a vast structure we call the solar system. But now we see it differently, with eyes opened by exploration, with minds expanded by understanding, with hearts moved by the beauty and complexity of it all. The solar system reaches farther than we can see, farther than we can easily imagine. But it also reaches here, to this moment, to this quiet reflection, because we're part of it. We belong to it. And in understanding where it reaches, we understand a little more about where we belong. The legacy is knowledge, but it's also connection to the past, through the ancient light of stars and the debris of planetary formation, to the future, through missions and discoveries yet to come, and to each other, through the shared experience of wondering about our place in something so much larger than ourselves. Welcome home. The journey outward has ended, for now, but the wonder remains, the questions persist, and the solar system, vast and layered and fading gradually into the galaxy, continues to reach outward in ways we're still learning to measure and understand. Rest now, knowing that we're part of something immense, that the sun's influence extends farther than the eye can see, but that its warmth is here, holding us gently, that the solar system has no single edge, but many, and that in the space between them, we find our place. The closing is a return to stillness, to the familiar rhythm of Earth's rotation, to the comfort of knowing that while the universe is vast and complex and full of mysteries, this small world is home. And home, for all its insignificance in cosmic terms, is where the story matters most. Because it's where we are, where we wander, where we dream of reaching outward, toward edges that fade rather than end, toward a universe that invites us, always, to take one more step, to ask one more question, to reach a little farther into the beautiful, endless dark. And so the journey closes softly, like a conversation fading into comfortable silence. We've travelled together through distance and time, through boundaries real and theoretical, through layers of ice and plasma and empty space. We've seen that the solar system is larger than we thought, stranger than we imagined, and more connected to the galaxy than simple diagrams suggest. And we've learned that endings are rarely sharp, that boundaries blur and fade, that the question itself sometimes matters more than any single answer. As you rest now, let these thoughts settle gently. The solar system continues reaching outward. Voyager continues its journey. The planets continue their ancient dance. And you, here on Earth, remain part of it all, held by the same gravity that holds distant comets, lit by the same star that illuminates frozen worlds beyond Neptune. The solar system doesn't end where you are. It begins here, with wonder, with curiosity, with the simple act of looking up and asking how far it all goes. Sleep well. The cosmos will still be here tomorrow, still vast, still mysterious, still waiting.